Thank you very much. So this was kind of the welcome and introductions, and I wanted to give you some context to the rich context. I am Julia Lane. I am a humble economist amid all these computer scientists, and those two words don't often go together, humble and economist, but this is where we are. So here's our goal. What we're interested in doing is, for a given data set, find out who else worked on the data, on what topics, and what results. So the motivating fact here is when you're, as a social scientist, when you're working with a data set, 20 years ago, there were only a dozen data sets that social scientists worked with. They were largely survey data sets, and you basically knew everyone who was working with them, and it was pretty straightforward. Over the past 20 years, social scientists are working. One of the exciting things about what the computer scientists have been able to generate is massive new amounts of data. But those data are no longer documented, and the information about who's used them and with what result is not available. So this kind of came up as a big issue when we were teaching the applied data analytics classes that Sophie, we've run maybe 300 government agency staff through these training classes, working with the new types of data. First thing the students would ask, the participants would ask, when they started working with the data is, who else has worked with them? What's the code? What's the documentation? And, you know, I was kind of going back in my memory banks and saying, well, let's go and look at this article or this article. That's not a very good way of building a scientific basis for empirical research. So we very quickly recognized that a major barrier to doing empirical research on these new data is finding this information. And so we talked to the Overdeck Foundation, Schmidt Foundation, Sloan Foundation, and they encouraged us to try and build a more scientific basis for empirical research, particularly around the social sciences. It turns out that there's a broader federal context. For the federal government, 3 years ago, there was a major push for supporting evidence-based policy. What evidence-based policy means is use data to inform decision-making. So the Murray-Ryan Commission was established in March of 2016. The Census Bureau was asked by the Office of Management and Budget to support the decision-making of the Commission. The Census Bureau asked us to build an administrative records clearinghouse that could demonstrate how data from different government programs could be combined and analyzed. We realized that just putting the data together in one place was a necessary but not sufficient condition. What you actually needed to build was the capacity to work with the data. And hence we started these applied data analytics classes. When the Commission did their final report of September 2017, they hosted this, they highlighted it. I'm going to call out Raid Ghani and Frauke Kreuter, who are my colleagues in crime in developing the applied data analytics classes and administering them, and my colleagues at NYU and UMD and U Chicago who made it happen. Turns out that the Commission's report had 22 recommendations. The House passed a Foundations of Evidence-Based Policy bill in March of last year. The Senate signed it in December of last year, and the President signed it into law last month. So that implements 10 of the recommendations. So what the work that we are doing here is very much, and Bryant is obviously here working on the evidence-based policy work at OMB and with the agencies. So it's very much consistent with that foundation's work. So when you're thinking about building evidence-based policy, there are lots of challenges, right? There are technical barriers in terms of cost and burden. There are human barriers. People worry a lot about, with these new types of data, there's very poor documentation in general. You don't have a federal statistical system putting the information together. And so, quite rightly, evidence-based policy that is based on bad data and bad analysis is not what you want to have, right? So you've got to figure out what you're going to do. So what this project is about is really how can we improve data documentation, how can we minimize the risk of bad analysis by having it replicated, many eyes on it, in of course a secure and confidential environment. So here's what we did, again with the funding from the Census Bureau and the generous support of many foundations. What we built was a technical environment called the Administrative Data Research Facility. And the basic idea here is the data are going to sit inside a secure facility, only approved researchers are going to have access. And what we want to be able to do is to generate an environment within which the data users can collaborate with each other. And as they're collaborating with each other, they provide feedback both to each other, to the data producers, to the data stewards about how the work is being done and so on. And so it's not a one-off, it's a whole research ecosystem that is being built. And one of our co-PIs in this project is Brian Granger and Fernando Perez who developed Jupyter notebooks within which collaboration can occur. So that's also part of the activity. So essentially the notion here is, why can't we build an Amazon.com for data, for public data? In the private sector, you don't need to be told that there is massive amounts of data that is being used to examine how people are moving, and it's being used for the private gain. What we're trying to do here is to build a data infrastructure so that governments can understand how to serve citizens better, to essentially use data for the public good, to coin a phrase that I think Raid originally coined. So the notion here is, when I land on a data set, and when I go to Amazon.com, I land and I'm looking at a book, and this is Charlie Catlett's from University of Chicago's slide, so I'm trying not to plagiarize him too much. But when you land on Amazon.com and it's got land on a book, it says, "Hi Eric, nice to see you. Here's something that is related to other books that you've seen. Here are books that are similar to the books that you've used. Here's what other people have done, and here are books like yours." So the basic idea is, can we build an Amazon.com for data where the results of the competition like this are going to be able to say, here's the data you've used, here are other data that are similar, and the Bundesbank's been very focused on this. You know, we can see in a particular publication what data are similar to this, other code, and as we're writing code that's similar to yours. So trying to build that not by top down, but building it from the community up. So that's the basic idea. So at the core, this is a metadata documentation approach. So the American Community Survey, human beings generate the metadata documentation. What we're trying to do here is have metadata documentation essentially generated automatically. So Eric Schmidt's vision here is to build a machine, to build an industrial revolution approach to automating the capture of information. This is an example of the way in which people collaborated in the class. You had someone trying to work on corrections data, and someone in the class said, what's going on with this variable? The variable doesn't make any sense. The person who is the data steward says, yeah, that's right, that variable is a junk variable. And you wouldn't know that from the data documentation. So what you're trying to do here is someone else says, here's some code that you can use. And someone else says, Rick Hendra from MDRC says, here's a really useful article you can work on. Okay, so that was kind of the activities that happened in the classes. And what we thought is, and this is how this rich context competition came about, is how can we engage, find the information from existing publications, and how can we engage the community in providing information? So, talking with Stu Feldman, who you'll meet later today, the basic idea is we're going to take a set of data, and what we're going to do is we're going to run a competition which is going to try and find within a given corpus what data are being used, who's using it, with what results and in what topic areas. So you're step one. Step two is, can we get the community to take the results that you guys have generated and curate them and say, this is right and this is wrong. And some of the judges in the room worked on the tools that essentially said for each one of your teams, yes, that's right, no, that's wrong. What we want to do is to automate that process and then rinse and repeat. So that's the basic goal. And then we'll feed it into our data model. I'm not going to go into that in too much detail. So what did we do? We generated a tagged corpus. It is actually Drew and Jonathan did a lot of work, and Ian Mulvaney at Sage Publications generously provided a corpus. We used ICPSR tags, and then we ran the competition. And thank you to the judges who were able to advertise the competition, some of the people who were coming in on WebEx who helped us to advertise it. And there were two phases. I'm not going to go into them in too much detail because I want you guys to start talking. The first stage was a very clearly tagged corpus of survey data sets where the task was to find those survey data sets. The second one was more of the Wild West, which is more in the vision of the broader picture, which is, can you find any data set in there? We then are going to be working, and John, and I saw that I mistyped your name, sorry about that. John Chase from Dimensions Digital Science has taken that first phase and tied it into publication. So in a couple of minutes you're going to see a demo of how that first phase work ties into understanding who's doing the work, with what results, and with what research. And digital science, of course, has done a lot of work with Figshare or metrics and so on. So there is a community out there that is interested in documenting data. Another way in which we're going to be working in terms of next steps is with Sage, our wonderful partners. We're expecting to work with some of the editors. So at the editorial stage, when you are submitting your paper for publication, we'll apply the model. We'll say, here's the data set. Is this right or wrong? And if it's not, what do you suggest? So that we start to build up a better model for your algorithms with the human curation of feedback. We're also going to build it in with the Deutsche Bundesbank, and we hope with our colleagues at the USDA and in the Federal Data Strategy. When a researcher onboards to do work with confidential microdata, and we're doing this in the classes, and you say, here's my research question, here's my methodology, here's the data sets I think I want, that what we'll be able to do is build a recommender system in there. Right now, if I've got a research project and I want to go into RDC and I want to find out what other work's been done, I rely on human beings, the research administrator, knowing what data sets there are and making those suggestions like as a human being. What we hope to build again with the work that you're doing, is information about all the other work that has been done that maybe the research administrator doesn't know about. The last piece is plugging this into Jupyter Notebooks. So my colleagues, our colleagues, Brian Granger and Fernando Perez, again with the generous support of our funders, when you go into Jupyter Notebook and you land on a data set, that there is a recommendation for a publication or an article, and the potential to suggest additional code. So, or provide your code that you have used on the data set and create DOIs for Jupyter Notebooks. So there's a lot of work. You represent the very first step. We're thrilled with the results that you've generated so far. We are going to be producing a book from the work that you have done, that you are, have provided us the information. Our tentative title is Where's Waldo? And we're doing that with Ian Mulvaney at Sage, and Jonathan Morgan will be the editors. And this is the tentative timeline. We're always aggressive on timelines, but I think this is important to get out relatively quickly. So we'll send out that follow-on information, Jonathan's right. So let's, with no further ado, let's move over to John and have him do a demo of how your work will be plugged into publications and so on. Okay. Does anyone have any questions while John's getting set up about the broader picture? So, Ekaterina Levitskaya just came in, and she is also one of the team who worked so hard on this. Make sense?
So, recently I've been a librarian. Recently I've been a librarian, and librarians are all about standards. So there's a lot of metadata standards and a lot of science.gov. You didn't really mention how this would relate to other areas of science.
That's a really good question. So there's kind of two ways of going about things, right? One is the establishment of standards and requirements, and I think that's part of the conversation with federal data strategy. There are principles and practices for metadata documentation. I hope I won't offend you when I say that one of the challenges with standards is people spend lots of time developing them, and getting people to adopt them, and I'm as bad as anyone else, is a separate challenge. So I think the approach here, and you don't see with Amazon.com anyone establishing standards and saying, you know, if you want to engage, this is what needs to be done. So I think the standards are certainly going to help improve the capture of knowledge, but there has to be some incentive for people to use that. So it may be that the standards evolve from the community. That is a little bit beyond my pay grade at this point, but I would hope to have a conversation going forward. Jonathan.
So we're trying to use schema.org as the framework in which we build our metadata, so that when there are standard things we can use within that standard, we use them. But then we're working with Jupyter right now to use that standard to exchange metadata about data across federated systems. And so we're starting to find the places where there aren't standards. So we hope to work with them to do that.
Yeah. Sorry, I thought you meant about
Well,
people
package
adopting standard. We will say that some of the health data were research, social science health research was a lot easier than other fields because they did have a standard structure in the project. So one thing that may come out of this is that the community gets more standardized. Yep, okay.
Only one word on the standard. So in our institution, we are building also tools for data curation and stuff. And we are using DDI standard in the background, so the user don't see what is happening in the background. So maybe it's useful for you too, or that I connect you to people in my institution who are working on this.
Yeah, I funded DDI when I was at NSF, so I've been a big supporter of that from the get-go. Getting people to adopt it, a priori is difficult, but the underlying infrastructure can be infinitely more successful.
All right, can you all hear me? Is this thing on?
No, you need
You
to
both?
go
All right.
to the WebEx.
I'm dual mic now.
Oh, you're dual mic?
Yeah, I think I'm good. Okay, so I'm John Chase with Digital Science, and we're really excited to be here today. I promise this will be my last Dimensions pun. I couldn't help myself though. So our platform is called Dimensions, and actually Dimensions was developed around the idea of putting the data in context. So yes, it's a little bit of a pun, but it's there on purpose. So Julia approached us. Feels like a few months ago now, maybe it was only even a few weeks ago, the time's been flying, to see what we could do to help to take the data that the teams here are producing and help to answer those questions that Julia mentioned. Who's working with the data, on what topics, and what are some of the results that they were getting out of the data. I'm going to try to do a live demo of essentially prototype code today, so fingers crossed everything will work. We have some backup screenshots just in case. But before I get started, I really want to talk about the data that we have to work with. I think I have the remote here. So when we're looking at data sets, data sets are great, they're interesting, but what's going on around the data set? So what we're doing here really is trying to tie the data sets to the publications, right? That's the work that these teams have been doing. Right now we have a small set of around 10,000 data sets or so tied to maybe 20,000 publications. What we'd love to do is attempt to take those data sets and tie them to a much larger set of publications. So currently in the Dimensions platform, we have about 98 million publications. So when you tie it to the publication, you can get a sense for, okay, well, who's working on these data sets? And you can do some topical analysis, perhaps, of the publications to think about, okay, well, what are they doing with these data sets? There's more context you can add, though. Once we have the publications, now we can take a look at the citation graph. So now we can start to get at maybe, what is some of the potential impact here? What are some of the more influential research that's coming out of these data sets used in publications? We can also tie publications then to grants. Who's actually paying for the research that's using this data? So maybe here we can identify, people that have a stake, organizations that have a stake in these data sets. Essentially, if you can tie to the publications, you can tie into a much more rich contextual network here, looking at altmetric, for example. What kind of public engagement is there around these data sets? So, the general public perhaps is not going into your data research enclave and interacting directly with the data set. And they're probably not reading the scientific publications for that matter. But journalists, the media is reporting on publications, and we can pick up Twitter mentions, news stories, really look at how is the public engaging with these data sets. We can look at how these data sets are influencing public policy. We take a look at policy documents, which are things like recommendations from the CDC on how to respond to disease outbreaks. Other sorts of documents that tie back, again, into the scientific literature, which we can then tie back into the data sets to get a sense for what kind of influence we're having. And then we can also look at other data like patents. Again, maybe get an idea of what are some of the downstream impacts of research around these data sets, and also a sense for the topics, and even in some cases, clinical trials. So what does this look like when you're actually looking at a publication? So here is an example of a rather rich context around a particular publication. So if we take a look at a publication, we establish links to clinical trials through references in the trials back to the publication. We can establish links to patents via non-patent literature citations from the patent to the publication. Similarly, in policy documents, we see policy documents actually citing publications. We can provide kind of a topical analysis of what's going on through different research classification systems. In this case, we're looking at the fields of research category scheme, which in honor of Julia is based on the Australia-New Zealand standard fields of research scheme. So there you go for that.
Australia.
New Zealand, Australia, sorry. Got to keep those right. And then we can also look at citations from other publications, citations to other publications, and again those connections to the supporting grants. So just by making that one connection between the data set and the publication, all of a sudden we can reach out into a much more rich environment to find out what's going on. So let's try to give this thing a spin.
Do you have any weights on this?
What's that?
Do you put weights on it?
Weights? Not at the moment here. I mean, we can calculate, say, citation-based metrics, right? Where, counting citations, that sort of thing. So yeah, you could derive weighted metrics. But in terms of the actual connections between the data, the individual connection between a patent and a publication, for example, we don't say anything about the context of how that citation or what that citation means. Right, it could be a throwaway reference, it could be critical. I can't tell you. But it's potentially signal though we're looking at. Okay, so if we operationalize this, what does it look like? That is not on the screen. Oh, this is going to be tricky.
Use the silent one, yeah, that's it.
Okay, I'll attempt to look at the screen over here, but we'll see how this works. Is there any way to get it to show up on this screen as well, or
I don't know.
All right.
Sorry about that.
F7 maybe?
Yeah, sometimes
That's fine, we'll make it work. So what we're seeing here, if I can maximize it, maybe. Okay, there we go. So this is the demonstrator prototype tool that we've put together. Taking a look at what we have here, we've populated it with data that was pulled from the ICPSR API provided to us by Jonathan and team. So what we have is we started from these 10,300 or so data sets. From these data sets, we looked at the links to publications that were manually curated in this particular data set. Ultimately, we're hoping to have these automatically, algorithmically generated links so we can go to a much larger data set. But we take these 10,000 data sets, and from there we identify 24,000 publications that have referenced those data sets. Then, from those publications, we can exploit all those other connections we had to other data types to bring in more information. So even though we don't have direct connections between data sets and grants, we still identified 5,000 grants here that are associated with the publications that reference those data sets. Likewise for patents, we have about 1,000 patents in this particular slice of the data, 738 clinical trials, and actually, maybe really interestingly for this audience, 4,000 policy documents. It's actually quite a bit more than I'd anticipated finding in this relatively small data set. And again, we don't have direct connections to any of these, but we can infer the relationships based on the fact that they're tied into the publications. So let's take a look at a publication. And here we go. So it's the type of data you'd expect to see around a publication. The basic metadata. Who are the authors? What are the abstracts? We assign some research categories to it. We have funding data associated with it. But then most importantly here, we have it tied back to a particular data set. And where things get really interesting in terms of asking and answering some of these questions is when we start to aggregate these different characteristics around these data sets. Generate the aggregate list of researchers to identify, well, who are all the researchers that are working with this data? And then also, well, in what fields of research are those people working? So an example of that let's take a look at one particular data set. I'm going to slice the data now. This is challenging. Okay, looking at one particular data set, I can't read which one we're looking at. The National Longitudinal Study here. who are the researchers working on this data set? Well, we know that there are several thousand publications related to that data set, so therefore we can identify all the researchers associated with those publications. So coming over here, this is a pretty reasonable pass at answering that question of who is working with this data. And in this case, with disambiguated researcher profiles, we can see that Kevin Beaver with 86 publications might be somebody you want to talk to if you're working with this particular data set. You can also do some interesting filtering. Not that much data in this tool yet, but as we get more data in here, say you're trying to identify somebody working on a topic of interest to you with a particular data set. What we could do is we could take a look at what are the research fields What are the research fields associated with the publications around this particular data set? And let's say I am a genetics researcher. So now we've limited those publications we're looking at to genetics publications that we've tagged as being related to genetics using this particular data set. And here we've identified the researchers who are presumably genetics researchers, or at least people whose names are associated with genetics publications. And then we could really start to drill down even deeper. Say you're looking for somebody local, you can buy a cup of coffee and pick their brain, right? We could identify, we know what their organization is, we know their affiliation, so we could drill down to the city level, and you could find someone local, maybe a neighbor down the street you could talk to if you wanted to really dig into what's going on around this particular data set. If you're trying to identify data sets, so this is identifying who are the people working around data sets. Another thing you may want to do is identify the data sets themselves that are of topical interest to you. So there's a couple of different ways you can do this. One thing we could do, and this is really what you can do today, is we take a look at the data sets, and we have title and we have some descriptive text around the data set. So we could just search for whatever our topic might be, right? Housing. All right, so here we've identified data sets that are potentially about housing. But the other way to go about this is to search for the topic of interest in publications and then see what data sets those particular publications are citing. So this opens up all new possibilities. So here we're looking at publications related to housing. I could do any keyword search I wanted here. And then if we go down and take a look at, well, what are the actual data sets associated with this subset of publications, now we can see the different data sets that are used to explore the topic of housing in the scientific literature. In this case, the panel study of income dynamics. This is not a surprising result. And rather than doing a keyword search, we could, again, use these predefined category schemes and say, I don't want to figure out how to do a good search for genetics, but we've got a reasonably good machine learning-based tagging system that's tagged all the documents in our database for genetics already. We can just use that category, say genetics, and then we get the list of data sets that have been used for genetics. And the last one I want to show so one of the things we looked at was on that previous slide we had the altmetric data. So the altmetric data is an interesting indicator because it can provide some insight, perhaps with caveats, into public engagement or into impact beyond just the citation network, beyond just scientists talking to scientists and citing each other's work. So this was kind of a interesting result. If we take a look at our publications here that are all tied back to data sets, last one. Sort them by altmetric score. So now these are all publications that reference one of these data sets, sorted by altmetric. And what's really interesting here, and you quite often see this with the altmetric results, is we're actually surfacing publications that usually have a couple of interesting things going on. One, they tend to be very new because altmetric data has not been around very long, and not many people are tweeting about articles from 2005. So here, the top article is this reduction in firearm injuries during NRA annual conventions, right? So I remember hearing about this, and the reason it surfaced here is because a bunch of journalists picked it up and ran with it, and there was all sorts of stories about it, people were tweeting about it. So that's reflected in the altmetric data, and we really see, okay, well, this is the kind of story that the general public, perhaps, is hearing based on these data sets. And what's interesting here, though, is we see this, it's only got 2 citations. So if you're using citation-based metrics to try to identify something like this, you're not going to find it, because it's too new, and quite often these types of articles don't end up getting cited all that much in the scientific literature, even though journalists are writing about them like crazy. So if we go in and take a look at, I can see, thank you. If we go in and take a look at the article, again, we can see that it's linked out to the Uniform Crime Reporting Incident-Based Reporting System, which is the type of data set you would expect to see in this particular instance. So that's basically it. Any questions? I hope you're all starting to see some of the potential. This is with 10,000 data sets and 24,000 publications. We have 100 million publications in our data set, 60 million of which have full text. So we're really hoping to see if we can bump these numbers up by a couple orders of magnitude or so.
Is this related to linked data? In other words, is it implemented in a triple store, or is it a relational database?
It's not. Well, I mean, technically in the back end, it's implemented in a bunch of Solr cores. You know, it's a search indexes. For analytical use, my team tends to stick all the data in a giant relational database. But we have worked with triple stores, and I mean, the data is clearly triple store friendly. But yeah, we've not implemented that.
So, for instance, Mellon Foundation has a Project Vivo to tag all the researchers around the world, and it would be nice to be able to plug that in so you had established, reliable metadata about each of the researchers. And you could do that more easily if it was all linked data.
Absolutely, sure.
And actually, if I remember, Vivo was initially funded through NIH, so an hour grant, because I was involved in it back in the day. But we should, in principle, be able to do that through the grants and maybe the PubMed, the researcher IDs.
Yeah, researcher IDs. They're not researcher IDs. When you're looking at, let's show you one of these keys, perhaps. When you're looking at a person, okay, so this one doesn't have this isn't the best example. But when you're looking at a person, we assign each of these an internal researcher ID, and then if possible, we associate them with any other external IDs that we know about to facilitate linking to other data sources. In this case, we have a NIH profile link, so NIH has something called a person profile ID, PPID, if you're really a data nerd like me. So we have these PPIDs associated with a bunch of our researchers, but then we also have ORCID IDs when we're able to establish those links to facilitate exactly that kind of linking.
Okay, let's get started. So I'm presenting the results and somehow our system. Who are ours? So let's say we are 7 people from the Department of Knowledge Technologies for the Social Science, based in the Leibniz Institute for the Social Sciences in Cologne and Mannheim in Germany. And as you see, our research questions in our department are related to information extraction, NLP, information retrieval, and semantic technologies. And we also have not only doing research, but we are a service provider for social scientists in Germany. So we are doing stuff around research data management along the research data life cycle you see on the top. So we are very related to what we hear this morning. And yes, GESIS is the largest European infrastructure institute for the social science in Europe. So why are we interested in this challenge, these competitions? We have already an integrated search engine for social scientists since now 2017. And as you see, we have a faceted search not only about research data, publications, but also on instruments and tools, and some other things like our like our library in the institute and our web page. And what is interesting, we already have linked information to publications from datasets and even to instruments and tools. And some log studies, which are right now will be published, emphasize the importance of this link. So the users use this. So our links are also hand-created or semi-manual created. We have some approaches which are more automatically, but we see the competition as a possibility to try new models, to use the provided data to build up new models or new ideas how to solve this problem. And so we have 3 tasks, and we interpreted them in the second phase as first dataset mention identification, then research field classification, and at the third point, research method identification. So the challenges for dataset mention identification, in my opinion, is mainly that there's no standard way, and even if there are now initiatives who wants to solve this problem, for example, by providing DOIs for datasets, which are somehow for computer scientists, then you only have to match. You don't need a fancy algorithm to get connections between publication and dataset. But on the other hand, we are not working on current data. Not everyone is using this. And if you look 10 years behind and have publications from 2004, you won't see any of those. And the main differences are, we figured out is that there are some researcher-dependent differences, like one is using only the short form or abbreviation, one the long form. One research community-dependent different style, like for example, we see in some publications of the Deutsche Bundesbank, the monthly statistics for outsiders who are not in the domain of economics is like, okay, it is some data, I don't know, but maybe for economists, they exactly know what is meant with these terms. And the third one, even broader domain dependent, like for example in the computer scientists, you for now often cite Git repositories where the data is persisted, versus some surveys in the social sciences. And the ambiguity problem is also a challenge. For example, in Germany we have one survey called Jugend, which is youth. So it can be anywhere, and if you find the term youth, you can't be sure that this is a data set, just as an example. What we wanted to do is, given the full text, find those mentions. But we want to use a supervised named entity recognizer to do this. So we use a neural network approach based on the standard implementation of a NLP tool called Spacey. But to be able to train this, we need fully annotated text, which means given the text, we need to know this word is the start of a mention and this one is the end. What we were given by the competition are 2 sources of somehow related information about this. One is the data set citations. This we used in the first phase. And this is our connections between publications given an ID and data set given an ID and a list of mentions. So in the first phase, our idea was we just remap these mentions to the full text. Let's do it like this. And then we have the correct context of the dataset mentioned. We do this publication-wise, that we can be sure that this is really occurring in the text. But some things didn't work well because we also have dataset mentions which are not linked in our data. So we can't be sure that every dataset mention in all the publications is inside these annotations. And we only have it for
2,500 publications from the first phase, including the test data. So in the second phase, we thought another minus is that the dataset IDs is just a subset of all the 10,000 datasets which are in the list of known datasets, I called it. Like it's the metadata table for datasets. And so in the second phase, we're concentrated on finding the correct full name of datasets inside our publications. And even in the publications we were suggested in the second phase. So not only like 2,500 documents, but all 15,000 we saw in the whole phase of the competition. Then after this remapping, we trained our classifier on this. So the remapping result is having full text annotated. And then you are able to have the right context. And if you have a good hand-curated annotation in this style, you are able to do something like dataset context analysis with it. Like looking at the surrounding of the mention, and this would open up much more possibilities to investigate the dataset mentions in the publications. As you see, we differentiate between strict and partial. These measures are based on named entity recognition. So we are looking at how good we are in finding the correct mention in the full text. And as you see, the partial one means we somehow get the right context, but not the right words. So there have to be at least one word overlap. But it's interesting for us because some mentions in the mentions list of the first phase are not in the same way. So sometimes the year is included, sometimes not. So this is a sign for us of how good we are in matching the right context. And as you see, the precision seems not to be very good, but on the other hand, if you see what the results are, these are results which are new in respect to not seen in the training set. And as you see here, for example, we are even able to find datasets which are not in the metadata table of datasets. Okay, then come to the second point, which is research field classification. Which we interpreted as given a publication, try to find the right research method which represents the publication the best. And we want to do it in a multi-label classification, treat it as a multi-label classification task, train a simple fast text model which seems to be very fast and quite reasonable results. But again, we have no data inside the competition. So what we have done is we use the data set which we have in-house, which is based on the Social Science Open Access Repository, SSOAR. You see it here, like you are able as a researcher to have a open access, to upload your papers as open access. And our team is also curating this metadata of these publications. So we have, for example, the classification social sciences, which we used. You have keywords from datasets, it's called. It's vocabulary which is produced in-house. And you have the abstracts, which some of them are English, so most of the publications are German, to be honest, but I think 1/3 is also English publications. So we used this data, which was like 6,000 publication abstracts in English language with 140 classes, and reduced them to to the labels which occur more than 300 times in our test and training set, trained a classifier on it, and get an F1 score from 52%, which is good for multi-label classification, I think. And we had 94% of publications which are labeled. In phase one, the ranking from the judges were quite good. The last point were the research method identification. We treated the same as the first task. So finding those mentions in the publication full text, which are able to describe the research methods the best. Our approach here was taken because, again, the lack of fully annotated data. We train a classifier on a different domain based on the semantic classes theory, model, measure, and tool. It was from the linguistic context, and then adapted to the social science by further training on a smaller corpus, hand-created corpus, and using gazetteers which are based on controlled vocabulary. I will talk to this on the next slide. And did a post-processing to enhance the precision and say, okay, it has to be an overlap between our controlled vocabulary and the results from our classification. So what we were using as a starting point was the given vocabulary from SAGE and expanded by a statistics glossary and also 54 further not seen manually controlled terms from our SSOAR corpus. And then you see results like this. The publication Double Jeopardy, Aging as Leveler, or President Health Inequality leads to the terms double jeopardy hypothesis, empirical tests, cross-sectional analysis, statistical tests, in-depth interview, which somehow reflects good. But, and the judges also says the results are looking good. So it's not perfect, but given the information that we don't have much training data, I think the results are quite good. Okay, the lessons learned is how to deal with sparse training data. So in other competitions, you normally have like a data set and you're just optimizing your models. But for this competition, the real challenge was to get the most of not so much training data. And this was a really inspiring process in our team to get ideas of how to solve this problem. And the other ones are how diverse citing culture of datasets is, and that gold standards make life much easier, even if you don't have them for training, but during development, a smaller test set where you can say, okay, it looks quite good and not just guessing. Okay, for further research, we want to use our methods for the pipeline on our internal SSOAR corpus. I didn't mention it, all the metadata from this corpus is openly available over an OAI endpoint. So you can, even if you want to try things on these classifications, you can just do it, crawl it, and work with it. Then combine dataset and research methods approaches we have developed during the competition, and using the knowledge gain of our participation within our GESIS infrastructure. And maybe joint work, maybe we can work together to have to create a reference dataset, create a reference dataset for identification. Yeah, we are open to this. So, and it would be good if it's possible for the research community, which is not somehow so involved in social sciences, to just play with this data. So maybe for research purposes, we can create something which others can work on too. Okay, I think that's it for me. I'm open for questions.
So I'll start with questions before comments. Why could you talk a little bit more about limiting to I think it was 44 fields? So how did you make that decision, and was it strictly necessary?
You mean for research field classification?
Yes, exactly.
Yes, we only. The problem is for those labels you have power law-like distribution. So most of there are some labels which are often tagged and some not. And to get good quality, we wanted to use only labels where we know we have enough training data. So somehow we are reducing the possibilities of our models because we are reduce the size of labels, but on the other hand, it's better for precision.
Right, and so my question is, where did the number 44 come from? How did you decide to make that cutoff?
Okay.
And while you're answering that, not to jump in, but jumping in anyway, while you're answering that, did you have an analysis that would tell if it was 48, if it was 50, if it was 32?
For this parameter, to be honest, we don't have this analysis, so it was just some try and error, but we don't have something to use for a publication.
Right, but so do you have any sort of qualitative,
So
like how
what-
bad was it
Yeah.
when you say took all the fields, even with one training example?
Yeah, what we did was analysis of selecting the right threshold, and there we tried to keep in mind two measures which are not like only precision and recall, but also how many publications do at least have a label, and on the other hand, how many of the publications at least have one correct label. Because it's multi-label classification, and you know that there's some inter-rater agreement problems here. You can't say if there is no correct classification, it's crap. Mostly it's a type of meaningful too. But these are the metrics we keep under control. Yeah.
Can you say a bit more about where that labeled data came from that you were using for that classification?
Okay, this label data for this task, for the second task, is mainly based on hand-curated data from metadata from SSOAR corpus. So the idea of SSOAR is give the researcher the chance to just publish their preprints or postprints as open access. And then it goes to a manual creation process where manual creators say, okay, this publication can detect with these terms from different vocabularies. And one of these is the social sign classification, which was the best meeting point for our task here.
But and then the labels are being applied at the document level rather than at the
document level, yeah. And for classification, we just use the abstract because in our training set. So we have a problem that we are training on another corpus than the one from the rich context competition. But I think the results show that there is overlap in topics.
If you would train, instead of on the abstracts, you would train on a summarization of it, you would summarize, how do you think it'll affect your results?
So we have not the possibility to try it on other things because some of the publications are not English but German, only the abstracts are English. And so we are reduced on this information about abstracts.
I'm curious, in both of these, in both the field classification and the data set identification, that a lot of the things you're showing sort of what worked. What were the types of, were the errors that you were making? Were they sort of errors that you would expect, or were you getting very strange errors in both?
Okay, there I can say something about the first place, because there we are matching with the mentions. And these mentions are very diverse. So sometimes it's like a sentence which is describing the dataset. Sometimes it's the full name of the dataset, and then in brackets abbreviation. Sometimes it's a year included, sometimes not. So, and there the difference between these values of strict and non-strict
partial and
partial precision differs even more than here. This was the results from the first, from the second page. Yeah?
I guess I'm more interested in if you get the ballpark, if you get the right area, that's good enough.
Yeah,
I'm thinking about it. Are you getting the context right, and the authors of the papers are using the same context to refer to data sets as well as organizations as well as other types of entities, and you have to kind of do more fine-tuning on the context, or is the actual noun phrase that you're extracting that's really ambiguous. Like, are your errors coming contextual problems? Well, are coming from your contextual features? Are they coming from
so
the
there
noun
are
phrase features?
some errors. So we are just training on dataset mentions. Yes, our model only have one class for the dataset mention, which is datasets. What we see was some structural problems with organizations, which are somehow wrong labeled, and the other one was, I think, no, I didn't remember. So this was one of the main problems to have a mismatch with other entities. That's true. So if you train this model, and that's so in future research, we want to first combine the research method with the dataset mention identification, because there's also an overlap of context, which is describing of what you are doing with what. To somehow be able, that the model can differentiate between different named entities. But if the problem is the data. If you have a good data set where other entities are labeled and also data set mentioned, you are much better able to differentiate between these different types. Yeah.
All right, you're at a disadvantage because you're the first group, and I'm going to ask the same question to every group, so they have a head start on you. But you've just spent a fair amount of time developing a system to answer this call that we have, and you did a nice job. But obviously, there's some things you wish you would have done differently. What did you do right, and what did you do wrong, and what would you do differently the next time around?
So. What we did wrong was long discussions about what should we do. We don't have any data. So we talk about like the first 2, 3, 4, 5 sessions. We sit there and brainstorm of what to do, and then every time we switch to or someone is switching to, oh, but we don't have the data. We don't. So the next time. If I'm restarting this from the scratch, I want to do it the other way around and say, okay, we don't have much data, so concentrate on this and do the best out of it. And the other one was, if you don't have any label data, even for testing, create your own small data set. And we did this, but only with a really small amount of time. And too often we are sitting there and have this feeling of, okay, we are just guessing and have no control. So this is the second point. Yeah.
You may want to consider looking into an area called weak supervision, but.
Yeah.
And so specifically, you mentioned that some of the things that the Spacey model was returning looked good, and so you could add them in as additional training data. And so other Googleable terms might be co-training and bootstrapping. Okay. People have a lot of names.
Yes, I just gave them one. You're right.
Yeah, exactly.
Yeah.
So you said at the beginning that the mentions was a more interesting problem for you guys to confront than the actual citations, for reasons of not everything is cited consistently. Do you have any thoughts on why you performed worse on the citation problem than on the mentions? I mean, I'm looking at the false positive rate here, which is pretty high on the phase 1.
Okay. The difference are mainly, so it's a different kind of data. What we are searching in the second phase was the full text and the full title. So it depends on what you want to do with this data. If you want to rematch it, it's somehow easier to match the full titles than some vague mentions like monthly statistics or something. Yeah. So this is a pro, but the con is. And the second one is you are comparing the data from our documentation, I think, or not?
I was just looking at the F1 score of the dataset citations component, which was 0.096. I don't know if you had it up on the slide there.
Okay. This one. Why are the F1 score values so bad? Yeah?
Yeah, that's a different one.
I think that's it's classification.
The second reason for these bad values, as you see here, this is research method identification. Yeah. These examples. These are all not in the labeled in the training data, but found, yes. And we have the problem that by remapping the dataset titles, we only remap things which are noun phrases, which means which have the right, which have a context. Mm-hmm. If you have dataset titles somewhere beneath a figure or something, then you probably don't identify it as a noun chunk, and so we're not remapping this. But you will find it with the algorithm as well, because you might find it because of the word overlap, and the model is seeing, okay, this is a cohort study, this might be a dataset, because of the words, not the context. But we thought it could be, so you see it's a bit of guessing again, but we thought if we find, if we are training on dimensions which have a real context, which means you have a context like this, where you have a sentence which is where the dataset is mentioned, then you are able to have a better generalization. This was the reason. And so, yeah, we think we don't have to point at the very high precision, but on having the right training data.
Ian and Frauke, I know you're in on the WebEx. Do you have any comments from them? Are we going to be able to pull Frauke and Ian in? Yeah, okay. So we may be trying to figure out how our judges who are on WebEx are able to comment, but I didn't want to come with it. Questions from other people here? Any other participants?
So when you did in the second phase, you searched for the full data set rather than text. How did you actually do that search? Like, were you literally searching for the full title? Because
Okay, so one, I can talk. I can talk about the problems we have here. As you see, we have here different dataset titles from one bigger collection, which is, in this case, the most cited dataset in the first phase. Like, I think 1/3 of the mentions we found in the first phase are concerning the ANES, I don't know how to pronounce it, in Germany I would say NANES, dataset. And as you see, there is in many dataset titles, and this is not only in the ICPSR data this way, also in other open availability dataset metadata lists, you have the combination of metadata inside the title, like the year where the data is collected and some subtitle of the dataset. What we have done is we just using the first part with a simple regular expression approach, yeah? Taking the first part and say, okay, this might be a title, then look at the results somehow, filtered like 20 terms which are too general and somehow based on things like New York poll, and then for a reason the poll is, we at the end want to identify New York, and it makes no sense, so we skipped it. Then we search for this, for the lemma of these terms inside our publications, and enlarge the area where we found this dataset title by using the whole noun chunk where we found it. So mostly the differences are that there are some years mentioned, which we include with this process. And sometimes we have the abbreviation included also. But for abbreviations, we have with this approach a problem because we didn't figure it as a, for our matching purpose. Yeah. Okay.
Thank you very much. I have to say, it was absolutely thrilling watching you guys figure out how to do this work. It was a very challenging exercise, so it's much appreciated. Okay, KAIST. So,
Yeah, it's obvious. Yeah, it's first thing. Well, no, like the obvious sector. If you've done information before, this will be the so going directly to CRFs and embedding. Right.
Yeah, maybe that's more a role of like the infrastructure that's available. Like
Whatever they have.
there are good tools for things, right? Or
to write your own.
Yeah.
Yeah, there are no off-the-shelf open source active learning inputs from
That's cool.
So, hello everyone, thank you for coming. My name is Coleridge I'm from Spain. I represent the KAIST team from Korea. So, our team is composed by Hong Ki-won, who is here, also Song Min Kao from Vietnam, but he couldn't come here today, and me. We are master's degree students at the School of Computing at KAIST in South Korea.
You probably need the mic, Laura. I doubt it's
Okay.
picking up.
Okay. Now it's okay? Thank you. So let me again describe our task. We want to obtain dataset names, research fields, and research methods from a collection of publications. And our approach is reading comprehension QA and entity typing for dataset names, TF-IDF similarity for research fields, and named entity recognition for research methods. So let's focus now on datasets. We use reading comprehension with our own generated queries, and we filter out the candidate's answers using entity types. So reading comprehension models is just basically a neural network that can reply to a question given a test. And in this text, we must have the answer explicitly. So, for example, given the query when is April Fool's Day, and the text, here we have the answer, the model can retrieve the answer, April the 1st. So in this complication, the text is just the publication, and the answer is the dataset name. So now we need to know which model to use and which queries. So we use document QA, and the most important characteristic of this model is the paragraph selection stage. So we have a query and the paper, we input both into the paragraph selection stage, and then we got a list of paragraphs. These paragraphs are like somehow relevant, and the answer is in one of these paragraphs. So then we input the paragraph with the query into the actual RC model, and we got the answer. So we use this model because we think that the dataset names are usually clustered in some section of the publications. So this paragraph selection stage is perfect for this. So now we need to know which kind of query we need to ask to the model. And at the beginning, we wanted to find some kind of general query that can retrieve all possible datasets, but this is really difficult. So for example, here we have, in the first one is something like time series study, so we need a query like what study. In the second example, we have something like survey of state court criminal appeals, so we need something like what survey. And the last one, we have national material capabilities dataset, so we need a query like what dataset. So it's really difficult to have a general query that can retrieve all possible datasets. So instead of creating this kind of general query, we try to create very specific queries, but with a lot of discriminative power. So in order to build this kind of queries, first we created a list of important query terms. We did it this way. Using the training set, we obtained the dataset name and the full sentence in which they appear. And we input this, the dataset name and the full sentence, into a query generation module. This will create a list of queries that retrieve this kind of data sets. And with this list of queries, we curated them manually, and we obtained this list of important query terms. These words have discriminative power because they come from queries that can retrieve dataset names. So we use this list of important words to create queries for each paragraph. So first we created a general query that with the paragraph selection stage, it's possible to get the important paragraphs where we have the answer. And then for each paragraph, we created a specific query that can retrieve the answer. So for example, for the paragraph number 1, we have a query like what data. For the paragraph number 2, we have a query like what survey or study. And in the paragraph number 3, we have a query like what statistic. So we want to retrieve really, we want to create really specific queries that can retrieve the right answer. And then we input into the actual RC model the paragraph with the query. So DocQA is able to retrieve right answers. However, it has a lot of noise. So for example, here we have table 1, psychosis, empirical, but we also have right answers, like here, this is a dataset name, dataset name, dataset name. So we need to remove that noise. We did some experiments and we realized that most of the dataset names usually has the same entity type. It's like something like organization or agency. So we decided to filter out by entity types. In order to do that, we use ultrafine entity typing. So this model can predict around 10,000 different entity types. So given this example, we use the Deutsche Bundesbank balance of payment statistic as our main source of data. This is an actual sentence from a paper. And given this sentence and the dataset name, Deutsche Bundesbank balance of payment statistics, we retrieve the entity type organization and bank. And in most of the dataset names, as I said, the type is organization. So we can filter out dataset names using this. So because of the entity types, we can filter out this data. We can filter out the noise. So we built a neural network classifier using these scores from the entity types and the score from the RC model. So in general, we have the RC model, we have the candidate answers with the score, we input into the entity type model the candidate answers, and we got entity types, and then we input the score from the RC model and the entity type into the classifier, and then we got the final answer. The final answer is the dataset name. So in order to analyze the results, we use an ablation test. So we wanted to know how important is each module, how power it gives to the final model. So in the first setting, we use just document QA. In the second setting, document QA with our own query generation module. And in the last setting, we use everything. So using just document QA, we had a low recall because this general query is not able to retrieve all possible data sets. So for example, in this paper, it couldn't retrieve anything. However, in using the query generation model, we got a high recall because we use really specific queries with discriminative power, and then we could get real answers, a lot of data sets. However, we got also a lot of noise because some queries, like for example, what study, can retrieve noise. For example, empirical study, it's because of this kind of query. And empirical study, of course, is not a data set. So finally, we try also with entity typing, and here we got a high precision and a high recall because we were able to remove the noise. However, it's not perfect, of course, so we still have some noise, like for example, here, here we have some noise. But still we have better results than only DocQA or DocQA with our own generating queries. So let's move on to research fields. The organization gave us a list of research fields with a hierarchy. So for example, we have health and social care, clinical medicine, and cardiovascular medicine. We search in Wikipedia just the leaf nodes of the hierarchy. So we'll search in Wikipedia this. And then our approach is to compare publications and Wikipedia articles using TF-IDF scores. So we retrieve as research field the title of the most similar Wikipedia article. So TF-IDF is just a measure of the importance of a word in a text. So because of this, it's really easy and really fast to compute. Let's move on to the analysis of this system. We tried with 20 random publications and we got the right answers for 11 documents. And actually the best thing of this model is that it can retrieve really, really fine-grained fields. For example, in the first one, the research field is nursing, home health, nursing management. It's really fine-grained. Among the problems we had, basically, when two topics are kind of similar, it gets confused. So for example, in the second example, we have inflammatory markers, and they also talk about cardiovascular problems. And because of that, it retrieved the field cardiovascular technology, which is wrong, but it's kind of similar. They talk about similar things. And in the last example, the real research field and the predictive research field share some subtopics. And because of these subtopics, it gets confused. But in general, the model we think is really good because it's really fast. We don't need to train a classifier, and it's just TF-IDF. And in the end, also by the judges, it was considered like quite good. I think it was the best one for 3 judges. So we think that it works because TF-IDF is able to know the important words of the text of Wikipedia articles and publications, so we can compare them. And also because in Wikipedia, there is a lot of articles about research fields. But of course, Wikipedia is not perfect and it doesn't have all articles about all research fields. So we have some lack of articles about some topics, like for example, data-driven decision-making in education. There is no such an article in Wikipedia. And also, as I said before, another problem we had is that when some topics share subtopics, then it got confused. So let's move on to research methods. Our approach to solve this is NER model. So this is basically, given the sentence, Apple CEO Tim Cook introduced the iPhone at Cupertino Film Center event, and NER model tried to tag Apple as an organization, Tim Cook as a person, and Cupertino as a location. We think that research methods are usually specific names, so we can model them as named entities. So for example, clinical trials, novel sampling. So we use the model called Tagger because this model can differentiate by context. We think that context is really important to define a research method. For example, in the first sentence, we have something like the key advantages of using content analysis to analyze social phenomena, blah, blah, blah. Here, content analysis are research methods. But in the second example, computers are increasingly used in content analysis to here, content analysis is not a research method. So the context is really important to find out research methods. And this model is able to use that context. So we analyzed again 20 random publications, and we got in 12 publications at least one right answer. However, it has a lot of noise. And another problem we had is that, for example, there are some research methods in which they are split by a word. For example, here, data were collected. Data collection is split by the word where. So this is a problem for the model. Another problem we had is that in the list of examples of research methods we were given, we had only around 600 research methods. So with this list, it's difficult for the algorithm to find new research methods. So we think that we need to obtain by ourselves more research methods or use other approaches like semi-supervised or unsupervised learning. So the challenge we had first is that we don't have enough training data to train an RC model. We think that if we train an RC model specifically for this task, we would get a higher performance. So because of this, we use a pre-trained model on SWAT. Another problem we had is how to create good queries to retrieve data sets. So in order to solve this, we created our own query generation module. Because of these two things, we had some noise. And in order to remove that noise, we use ultrafine entity typing. Another problem we had is how to identify research methods, because it's even difficult for us to decide, okay, this is a research method and this is not. And in this paper, they're using this and they're not using this. So it's even kind of difficult for us. So for a machine, it's of course even more difficult. So our future work is based on the following hypothesis. We think that dataset depends on research fields and vice versa. So for example, in question answering, as a field of computer science, the most commonly used dataset is a squad. So two papers using a squad are very likely to be in the same field, Q&A. So we want to build hierarchical clusters of papers with the same research field. So for example, in computer science, we have the cluster Q&A, and we would have papers like paper 1 and paper 2 which are using the same dataset, squad. And we also think that a cluster will have papers with the same research field and similar datasets. So in the cluster of Q&A, we have papers using the squad and trivia QA with actually similar datasets. So we think that we can recommend to data users similar datasets. So for example, the data user will input into the system a new publication. Because of our research field retrieval, we can cluster it correctly, and then we will be able to recommend to the user datasets because of the clusters. And in addition to this, we also think that we can recommend to data producers research fields with small datasets or maybe not enough datasets. So let's suppose that, for example, in this cluster, there is only one dataset. So we can recommend to data producers, okay, in this research field, there are not enough datasets. So we can work here. So in sum up, we created a query generation module for retrieving dataset names. We also created a dataset classifier using scores from the RC model and entity types. We also propose a model to retrieve research fields using TF-IDF similarities. And finally, we propose a research method retrieval using NER. So that's all. Thank you for your attention. And if you have questions, feel free to ask.
Questions from the council?
So first of all, I work on question answering, so it's very nice to be doing question answering. So I'll apologize to everyone else in the room, so I'm going to ask a bunch of questions about the question answering component.
I'll sit down.
Take it now. So you said that you used a trained model for squad. Can you talk about, there are other models that you could have used. Could you talk about why you chose squad and not squad 2.0 and
well, we used document QA because we had the hypothesis of...
right, so I totally buy that, but why specifically squad? So a model's trained on squad and not, say, squad 2.0.
Basically, it's because it was one of the models it was provided by the organization, LNLP, and also we tried with 4 project models they used, and the best result we got it was with this model.
Okay, yeah. So did you always take the output of RC? So whatever it output, you took it. Okay, so when you were making the decision in the post hoc filtering, did you use the span scores as a feature?
In the classifier, we used the score of the RC model, yeah.
Okay, and so which score? So you get a score for the left edge and the right edge. So which scores? If all both?
It's the final score of the model. So the candidate answer has a score, and we use this score.
Okay, so summing the two sides.
Yeah, it's like span score, yeah.
Okay, so the entire span score.
Yeah. That's
Okay,
the entire score.
and you didn't do it separately for left or right.
No.
Okay. Okay, and yeah, so I guess to sort of synthesize what I'm trying to get at with some of these questions, in question answering, there's now sort of a movement to not always trust your model and to accept that sometimes there won't be an answer present in a document, and so that's why we have Squad 2.0. So that might be something to take into account in the future, to have a model that explicitly knows, I might not be able to find an answer here. Okay, I will stop talking.
Yeah, microphone for a bit. Yeah, I think what I liked about sort of your sequence of, we tried this, we looked at the results, and we thought, you know, we have 0 recall. So we should do something. Well, now we have too much recall. So you kind of engineered it as opposed to starting with, here's a thing that we have. You really did a good job of sort of finding the problems. Looking at data is novel in computer science. And so that's a really good. I had a couple of questions. When you say sort of you just use document QA, what was the query in that case?
We use at the very beginning it was something like which data set they use,
Okay,
or
so
which survey, and then we tried to combine different keywords like which data set survey, and then at the end we generated a kind of long query using all these kind of important words.
Right.
This is just the general query for the paragraph selection stage.
Okay, so the first one was just hand-built queries, and then the query generation was your looking at the training data, and then you were using the neural network to train from the scores as well as the queries. Got it. In the part of, I'm curious on so I think a challenge is that when you're talking about also the last part you mentioned, like the co-clustering type thing, right? You've got data sets and you've got fields and you can use them.
Yeah.
I think there are sort of different types of those, right? So one thing to be cautious of there is what you end up finding is if you're reading a methods paper, then those data sets are interchangeable, right? People are using it to validate a method. So let's say you built a new entity extraction system. Everybody's using these 5 data sets, and you can now recommend, if you use this one, recommend that one. That makes sense. And if these data sets are being used, they're mostly only being used for entity extraction. But now switch over to social science, where you're trying to figure out how certain behaviors happen, and you're linking multiple sources of data together. And the novelty is not in the method, and so I think that kind of method will give you really good results for methods papers. But for kind of understanding and, you know, nobody has used these 3 data sets before together because they weren't linked together. Or a health data set and a wage records data set and a criminal justice data set together could be used by any of these fields, or a 4th field to say, how do these things link together? So I'd be a little bit careful there on separating because then you just find that the boring papers or the boring data sets and the novelty goes away because you can't link these. So I think a little bit of understanding of what type of paper is it? What is the goal of the paper, or maybe the research field even, and connecting with, you know, kind of doing some sort of clustering there might be interesting.
I was, in some sense, going to comment very similar on the first part. You guys basically did I liked the approach because he said it's a branch and bound. I basically go and cast a wide net. The wide net basically does something. It gives me a lot of opportunities, but a lot of junk comes in it as well. So let me bound it again, and then I bounded it too much. In some sense, in the world of physics, they'll call it simulated annealing. It's the same kind of approach, kind of go out wild and then go get lucky. But my question to you is, given that, so your first, in phase 1, you guys didn't do so well. Phase 2, you guys did very well. What is the magic secret sauce that bounded it better and branched it better between phase 1 and phase 2?
I think it's the addition we did to document query, to the RC model. Because using just the RC model, we couldn't retrieve like all possible data sets, so the recall wasn't that good. But then, because of the query generation model and how to remove that noise, I think we could improve the performance.
So basically, it's exactly the engineering issue. You basically had a lousy recall to start with, so you can't do very well. And then you had a big recall, and you expanded, and then you managed to prune it down to increase your precision. Fine, I'll buy that statement. All right, so now I'm going to ask you. So now I'm going to ask you the same thing I asked everybody, the first team. It will be eventually everybody. What did you do right? What did you do wrong? And what would you do differently this time around?
Well, for the right things, maybe research fields, because the idea is really simple and it worked, I think, pretty well. So I think this is the right thing we did. And about the wrong things, I think our approach to resolve research method wasn't that good because at the beginning we focused a lot on the dataset names. So we didn't spend so much time on research methods. And because of that, when we started doing this, we also had the problem of, oh, we don't have enough data, what we should do. And instead of trying to look for more data, we were trying to work just on this. And I think trying to look for more data would have improved our results.
So what would you do differently now? You'd look for more data on the onset, is that what you do?
Yeah, try to get more data and trying to also to understand better the data. Because we think that there are a lot of
So you agree with Rai then? That's what you would do? You'd basically focus on what data you've got and how you'd use it?
Focus more on what data we have and how we can implement it. Any comments you have?
Well, I think the other thing that we did wrong is that we couldn't train our parsing model.
Yeah.
Well, that's because we believe that's because we have like the data instances. And if we have enough data set, we could train our parsing model. And I think we could be able to generate some vector representation of queries. And we may even try to train the query and try to make a vector query during the training process. So in order to catch the contextual information around the data set. And actually that's one of the reasons why we choose our model, because our model based on sequence model can model the contextual information. So, and we believe there's some specific patterns of context surrounding data sets.
So I very much like what you guys did was this apparently a systematic failure analysis, because you really moved from not doing so well to doing much better. So well done.
No questions for me.
One question you can ask by Mark. Says, she very much appreciated your idea for the methods classification. What type of input training data do you think you would need to reduce the noise that was in that methods classification?
Well, actually, I think the input data should be more precise in terms of definition of research method, because we see some research method like reliability or hypothesis in the training data provided by the application, and we believe that they're not research methods, so we are getting confused to what was the research method. So if we have training data with some strict definitions, then it will be more accurate for training.
Any comments from the floor? Okay, well, thank you very much. Terrific. Let's take our coffee break now. I would like to recognize Josh Greenberg, who just came in from the Alfred E. Stone Foundation, and then we saw you heard from Danny Boroff from the Stone Foundation last night. Again, another one of our sponsors, and thank you very much for funding this research. Okay, great. Okay, let's take our coffee break. Start again at 11:30. Fantastic.
Coffee breaks.
Now we're going to go to the last two presentations from the University of Paderborn and then from Alan AI. We now have Ian and Frauke logged in over WebEx, so they'll be able to ask their own questions. So, we can come out here.
Hello everybody, I'll reintroduce myself just in case you would have forgotten. I'm Richa Jalota. I'm a developer in the data science group at Paderborn University, and on behalf of my team, I'm going to present our approach for the rich context competition. Starting with an overview, our pipeline consisted of three main components: pre-processing, fields and methods identification, and dataset detection. The pre-processing module read from the publications and generated some files. These files, along with the fields and methods vocabulary, were used to identify fields and methods in the publication text. The information about the research fields was then passed on to the dataset detection module, which, together with the dataset metadata, used to identify the dataset citations and mentions. Now, this was just a high-level view of what we did in our approach, and now I'm going to delve into the further details of each of these components, starting with the pre-processing. So while we were inspecting our training data, we found that there were many articles that hadn't been converted properly into text. They mostly contained of non-ASCII characters. So intuitively, the first step of the pre-processing was to generate text files from PDF properly. And for that, we used an open source tool, PDF to text, from Popular Utils. Next, we handled the words that got split by hyphens, removed all the irrelevant content, and extracted the main sections like abstract, keywords, summary, methodology, so on and so forth. Having done that, we extracted the noun phrases from each of these sections. The role of noun phrases will become clear in our next segment, which is fields and methods identification. Now, for identifying fields and methods, vocabularies for us played a very crucial role. In phase 1, we used the vocabularies that were given to us by Sage Publications, but in phase 2, we experimented a bit. So for research methods, we created our own...
Risha, would you wait a second?
Oh, no, they can just review that in the train. Oh, no, my fault.
Okay, wait a second.
Okay.
Okay, we're good.
All right? Okay. So for research methods, we created our own vocabulary using Wikipedia and Wikipedia. Basically, we went down the hierarchy of subcategories belonging to the category statistical methods. Then, we fetched all the relevant statistical methods that were present either in the subcategory or the category itself. Our aim was to fetch all the relevant statistical methods and their the labels of the methods and the description from Wikipedia. Once we had the labels and descriptions, we gathered their noun phrases. For research fields vocabulary, we used the same vocabulary as was given to us by Sage Publications and did just two things to it. First, created a list of irrelevant terms, and second, extracted noun phrases from the description of labels that were present in the vocabulary. Once we had the noun phrases from both the research methods vocabulary and research fields vocabulary, we generated vector models for each of them and used these models for identifying methods and fields in the publication text. Now, coming to the identification of methods, we first found the closest research method vector to the noun phrase vectors using a cosine similarity. Then, we computed the significance of the recurring methods using inverse document frequency. So, for instance, if a research method called z-ratio was occurring very frequently in the result, then we computed how significant it was to the publications using this IDF. And we assigned each research method a weightage. Then we reran the algorithm to find the closest research method vector, and based on the weighted cosine similarity, selected the highest vector with we selected the pair with the highest vector as the research method of the article. Now, coming down to the research fields identification, for it the process was a bit simpler. We selected the top 10 research field vectors from the publication text and compared, and then the pairs that had a similarity score less than 0.9 were filtered out. If the top ranked term was not present in the blacklist that we had created earlier, then that term was marked as the research field of the article. Now, as I said before, the information about the research field was passed on to the dataset detection module, which is the last and final component in our pipeline. For dataset detection, we combined two approaches. First was a simple dataset mention search. For this, we selected all the unique datasets that were present in the dataset metadata that was provided to us in the training set. Then we searched for all these datasets in the publication text. We then computed the frequency of the predicted datasets, and as you can see, there were certain datasets that were getting predicted a lot more than other ones. So we removed all those mentions that lied in the higher frequency range of the predicted datasets. In our next approach, we trained an entity extraction model using Rasa NLU. Rasa NLU is an open source tool to train models for intent classification and entity extraction. We tried two configurations for it. One, we used the 2500 labeled publications from the phase 1 training corpus, and our second configuration had 7500 labeled publications from the entire phase 1 corpus. Now, once the model was generated, we used this model to find entities in the pre-processed publication text, and only those entities were considered as datasets that had a confidence score greater than a certain threshold value, and those that belonged to the research field of the article. So that was all that we did in our approach for dataset detection and fields and methods identification. And now very important part. Once we had the results from both the approaches, we combined those results, but keeping in mind to remove all those mentions that occurred in the higher frequency range that we had calculated in the first part, right? So yeah, that was all that we did in our approach for dataset detection. And now coming down to the results, the evaluation part. So among many others, we compared these 4 approaches, and we did a quantitative evaluation against the validation dataset. So as you can see, for the Rasa-based approach, even when we increased the number of samples in the training dataset, there was not much significant improvement in the performance. But when we tried a combined approach, the performance was improved by around 20%. A reason for that could be that the labels in the training dataset that we had were not uniform in dataset mentions. So, yeah. Now coming down to the qualitative evaluation that we did against phase 1 holdout. For publication that had keywords such as cycling for transport, leisure, and sports cyclists, our phase 1 model gave health evaluation as the research field. However, our phase 2 model went a little deeper and gave public health and health promotion as the research field of the article. So in general, our model for phase 2 did a deeper analysis of the text and gave more granular results. Same was for the methods, in which we had changed the vocabulary altogether and used the vocabulary from Wikipedia that was curated by ourselves. And for publication that had keyword thematic content analysis, our phase 1 model gave thematic analysis as the method. However, the phase 2 model went a little deeper to predict C-deck correction as the potential research method of the article. Now, there were many challenges that we encountered during the entire process, starting from the pre-processing. The appropriate extraction of text from PDF was a challenge, keeping in mind the varied formats that were present in the PDFs. However, we could pass that using our open source tool PDF to text. And then came the extraction of specific sections from the text. And it was even more challenging to get the text from the articles that had no explicit mentions of the key terms like abstract, data, methodology. How do we say that this text is relevant if there is no annotation about it, right? So we did whatever pre-processing we could for such articles, and then ran the pipeline on the pre-processed text, whatever we had out of the pre-processing. Next, as I said before, for dataset detection, to train an entity extraction model, it was hard because there was not enough uniformity in the labeled data. coming to the research fields and methods, for us, vocabularies played a very major role. And we found out that in the vocabularies that were given to us by Sage Publications, there were many terms that were either polysemous or were too high level to be categorized. So when we were looking for some other vocabularies, we found out that there is a non-availability of open ontologies for methods and fields, and hence we switched to the manual curation using Wikipedia and DBpedia. Our future vision is in the same direction. As the number of publications that are rolling out every year is increasing tremendously, we can see here that this graph is from only medical sciences domain, but as a matter of fact, we know the scenario is the same in all other domains of social sciences and sciences. So we also know that research in one field drives the research in another field, and hence we want to create a giant global knowledge graph comprising of all scientific domains. It should follow the concept of never-ending learning. That is, it should be able to continuously update itself with the incoming articles. Next, it should be distributed. So having a centralized data center for it, data store for it would be just impractical, and hence it makes sense to have a distributed way of storage of the knowledge graph. Then the knowledge graph should be self-feeding, meaning it should be by itself able to extract all the desired information, fields, methods, data sets, all the geospatial information about the authors, all the metadata about the articles by itself. And having said that, it should also be self-repairing, because we know the trends in research change very, very often, and if the priors change, then we have to change the way the classification happens, right? And in this, having said that, humans would play a significant role in guiding the knowledge graph to learn in the correct way. So the knowledge graph should be weakly supervised. And lastly, and most importantly, it should have a standardized access via Sparkle, linked data fragments, question answering, or even search engines. So having such a knowledge graph would significantly help not only the researchers, but it would also eliminate the need to manually update or create the ontologies for methods, fields, and other metadata. And having such a knowledge graph would also empower and enhance interfaces which work in the scholarly domain of giving out research information to the scientific researchers. So this is one of our interfaces, and it currently supports only entity-based search, keyword search, and place-it search. You can check it out on the link that's given here. However, I'm going to show you a very quick demo of it. Okay. Moment. Yeah. So if I do this entity-based search, then I get a lot of entities with the name, and yeah. So now here we can have the geospatial information of this entity, like where the entity is doing his research, where he is affiliated with, who are the top co-authors, and what kind of publications he publishes. So yeah, you can try out the other features of this interface as well. But our end goal would be to empower such an interface with the giant knowledge graph and to bring out all the information and all the capabilities of the knowledge graph in such an interface and make it even more powerful to make the life of researchers like us a little bit easier. So that was all from my side, and this is my team, and thank you. Any questions? was just my lousy mouse skills.
Okay, so I appreciated the presentation and the focus on the error analysis. That was very nice to see. I also like that you talked about sort of the what we often sweep under the rug, the messy necessity of data wrangling and pre-processing. And I just in terms of lessons learned, what do you think is the right level of abstraction to work with this kind of data? And so should it be PDFs? Should it be a different form? Should it be raw text? What do you think is best?
I think having the data annotated would be a great help. But I'm coming down to it. Having it in XML.
Excellent answer. You asked the question.
Yeah.
You gave an excellent answer.
My answer is not yet complete.
Yes.
My answer is not yet complete. I mean, having it in XML format would be great, but as we know, the content that we had was typically varied. There were 3-columned articles, there were 2-columned articles, and it's not, most of the times it's not very convenient to work with the XMLs in such a format because the kind of tools that we have right now don't really keep the formatting intact and all the text goes haywire. So I think working with text was a lot simpler. We tried a lot of approaches to convert text into more developer-friendly format. But yeah, text would be great and properly converted text. Yeah.
Yeah, I guess one of the questions is similar. But I think the part that I'm trying to think through is in your. There's a lot of things that you did, especially in sort of the classification part, that just seemed very ad hoc, right? It's you did, I think, the cosine similarity, and then you looked at IDF, and then you weighted the cosine similarity with the IDF, and then you find similar things again. And do you know which one of them were? Like, do you have a sense of which of these things worked? Which of these things were just there because you did them?
So we initially started out with just finding the cosine similarity and between the noun phrase vectors and the method vectors that we had. And we found out that many a times the terms were getting repeated and the model was biased towards certain methods and not towards the others. So we saw the need to normalize, and IDF gave us the way to just break through the biasing of the models and to predict the methods correctly. So that was just based on our experiments and trial and error.
Okay.
Yeah.
And then for when you're doing that, I guess in all of these, one of the questions is, you're picking the threshold for classification.
Yeah,
right?
yeah.
Was that eyeballing it? Was it looking
That
at the
was-
precision recall curve and saying, I'm going to stop here?
That was also based on trial and error. We tried a lot of different values for it, and we found that the values that we chose, there was a certain value that we chose, right? So that value worked, and that gave better results than the other
When you
values.
say, when you say worked and better,
Yeah.
what's
So
were you
data,
going for recall? Were you going for precision?
we were focused on getting the F measure right, F measure better, and bringing down the number of false positives in dataset detection. So yeah, setting the threshold value. For dataset detection, we had set our threshold value as 0.62, and we found that setting it to that value was keeping our false positives down and we were not compromising with the true positives as well, keeping it that value. Yeah. So we had to find a balance between that. Yeah.
If you can go back to your slides, there's a slide that you have on between combined. Go back to the results slide.
Yes.
No, you just passed it.
This.
No, next. Table.
Okay, yeah.
All right, so you have here on the table, you've got your standard precision recall F1, that's fine. And you have this RASA base with the 2500, and it was 7500, and there's no difference whatsoever.
Yes.
And then you basically have the combined, and the combined is obviously much better. But again, there's no difference between 25 and 7500. I mean, I'll grant you that definitely the combined was dramatically better than the Manila RASA approach. But the parameters seem to be irrelevant to this.
Yes.
Why?
So as we can see here, the RASA-based approach didn't even work when we were increasing the number of samples to
But
it,
it's
right?
also true for the combined.
Yes, yes. So in the combined approach, as I said before, while we were doing a union of the results from both the approaches, we filtered out the results from RASA-based approach based on this frequency graph. So yeah, if the mentions that we got from RASA lied in the high frequency range of this frequency graph, then we eliminated that.
Right.
And that is why we got basically the same results on both of these approaches. Yeah.
I guess the question is, what if you took 250?
Right. So my next
Would it be
question.
the same?
Right. So my question, my comment was going to be, I guess it takes you longer with 7500 than it takes with 2500.
In terms of training, or
Yeah.
no, it took the same amount of time because I mean approximately. Because even for the 2500 publications, it took us around 17 to 18 hours and to train the model.
So now, if you
And,
since you look and you say 7500 to 2500 is a factor of 3, and maybe I can go from 2500 to say 800, another factor of 3. Would it make any difference? Because it seems getting larger didn't make any difference. And then obviously the next question from 800 to say 300. And I'm just curious if there's a.
But then I would say the model won't really learn well because
So I'm
after
looking
a
for
certain.
where would it start learning well?
I think the problem for us was in the uniformity of the mentions that were there in the training set that we had, and that's why it didn't perform so well on even the 7500 publications that we
answered
did.
my question.
That is because
You should stop. You answered the question. Because my next,
Okay.
what I was leading you to is there's got to be a reason why it doesn't do it, and you gave me the. And I thought it was because of uniformity, and you gave me the answer right away.
Yeah.
It's good enough.
Okay.
Last question for you then. Nicely done. Go onwards to do this kind of stuff again. You answered it beautifully. Next question for you is, like everyone else, what did you do right, wrong, and what would you do differently now?
What we did right was trying and testing out different settings and pre-processing, because for phase 1 we used the same text articles that were given to us, but while inspecting the results, we found out that for some articles our models didn't even generate anything, and the question came why, and then we looked into the articles and found out, oh, there's such a bug there. So yeah, that was the thing that we did great. And what we would want to try now is active learning, keeping humans in the loop of identifying the information, and also trying out different embeddings, because we just tried out word2vec, and now we would want to try and increase our approach for embeddings. Yeah.
One question, you talked a little bit about the blacklist generation. What was the motivation for that, and what was your approach? How did you create that?
The blacklist was created after we got the evaluation results of phase 1, and yeah, because the vocabularies that were provided to us, they, as I said, they had a lot of polysemous words, the words that were really ambiguous. So there was no clear demarcation between research fields and methods. I mean, quantitative evaluation in psychology is a research field, but if our model pointed out to that field, then you can't really make out, like, if it's a research field or method. So yeah, that, and there were some terms in the vocabularies like mixed methods, analysis, content analysis. So that didn't really give out the information of what field it lies in, right? So we
What's a
created
rough
a
order of
blacklist.
magnitude of what percentage of them were added to the blacklist? How big was that blacklist?
Not a lot. I guess just around 3 to 4% of the terms that were present in the vocabulary. Yeah.
Thanks.
So, any more questions?
Question from the internet.
Okay.
Ian Mulvaney of Sage would like to ask if you are aware of Pelagios Commons, which is a geo-based knowledge graph for archaeologically related materials. So, there you go.
I didn't know about it until now.
Yeah, I have a question too. Can you guys hear me? Yeah, okay, great. You said at the very beginning that you paid attention to the different formats the text comes in. I was wondering if you think your models would have benefited from prioritizing different sections of these research papers differently. So, there's a data and method section, there's sort of an inherent logic in these texts. And do you think you could restructure what you did to use that piece of information in addition?
Yeah, we actually used these sections to determine the fields and methods. So for example, to determine the method of an article, we focused more on the methodology or the data part of the article. And for research fields, we focused more on the title, keywords, abstract, summary, such parts. So, and also the JEL classification code if it was present in the article. So, yeah. So we did give a weightage to some specific sections based on what we were doing. And yeah, that was all.
Okay, great.
Thank you.
I saw you use the Rasa NLU. Do you use the Rasa core also, or?
No, just the Rasa NLU.
Just to entity extraction.
For entity extraction.
Okay. Have you thought about use the core to predict the next step or the result based on the past?
Because we just had to identify the data sets. Because in our problem, we just had to identify the data sets. We just used Rasa NLU to train the entity extraction model, and that was all that was needed, yeah, for this research problem. So any more questions? Seems like not. Thank you so much.
I think, do you have your mic?
Hello everyone, my name is Daniel King. I'm a pre-doctoral young investigator at the Allen Institute for Artificial Intelligence. The rest of my team was Sachin Gururangan, Christine Betts, Isabel Taghi, Walid Amar, and Madeline Van Zoylen. Briefly, a little bit about us. We all work at the Allen Institute for Artificial Intelligence, where our mission is AI for the common good, and we do a lot of AI research to this end. Specifically, we're on the Semantic Scholar team, which is an academic search engine, and the Allen NLP team, which is a Python library for natural language processing research. And the relationship between our work and this competition is that, so as I mentioned, Semantic Scholar is an academic search engine, and the goal is to help researchers do more efficient and more effective research by augmenting a paper with extracted and external content. So this is things like extracting images, counting the number of highly influential citations, linking GitHub repositories, extracting entities and relations, things along this line. We don't currently have a dataset entity in our search engine, and obviously this would be a powerful and exciting addition if you could search over datasets or look for the state of the art on a dataset or other research on a dataset, kind of like the rich context tool is intended to do. So as you've heard a few times, three main components of this competition were dataset extraction, method extraction, and field of research prediction. So I won't belabor that. We'll start with our approach to dataset extraction. So the data that we have about 10,000 datasets in a knowledge base, and each of these datasets comes with a brief description, a list of subjects, its name, and a unique identifier. And one thing to note is that many of these data sets share very similar names. So these are 3 example data sets, and there are many more that have titles that look like these. And in addition, these data sets can all be referred to using the same text. So monitoring the future could refer to one specific one of these, 10 of these, all of them. This makes the task of linking to data sets in the knowledge base much more difficult. We also had a 5,000 paper training corpus with the data set mentions annotated in them. So this corpus had about 10% of the data sets from the knowledge base. And an example annotation looks something like dataset X is referred to in paper Y as American Community Survey. And so as other presenters have noted, these mentions are not actually tied to the actual text. So if you want to get labels in the actual text, you have to search the text for the mention, and you may get, say, like 20 appearances of this text in the paper, and then it is not entirely clear which of those mentions is like a good example of dataset usage. Additionally, there's an element of subjectivity in these labels, so they were done by humans, and in particular, dataset usage specifically means that the paper used the dataset. It doesn't just mean that the dataset was referenced in the paper. And so even sometimes looking at it as a human, it's not entirely clear where the line is between used and referred to, and it makes the task more than just like finding a data set that's mentioned in a paper. You also want to learn what it means for a data set to be used in a paper. So the task definition here is you take as input a paper and the knowledge base that we were given, and you output data sets that are used in that paper. So this is both data sets that are linked to the knowledge base that we were provided and data set mentions that are not necessarily data sets from the knowledge base. So this fits into a common information extraction framework, and you've seen some of these components in other presentations. So named entity recognition is the task of identifying named entities, which can be loosely thought of as proper nouns in text, and identifying the type of this entity. So this would be something like a person, a place, an organization. For our task, there's only one entity type, it's just data sets. So it's just, the task becomes just identifying the actual mention from the paper. And then after this, performing entity linking to connect these mentions to the data sets in the knowledge base. So in a more general setting, this might be attaching the text Obama to Barack Obama's Wikipedia page and getting the right Obama. And so in our case, this is linking data set mentions to the knowledge base that we were provided. And one difference here from kind of the normal setup of entity linking is that a single mention can be linked to multiple data sets in the knowledge base, whereas in the more general formulation, usually a mention maps to one real-world entity. In our case, it might be like monitoring the future surveys 2000 through 2010, and then that's 10 different data sets in the knowledge base. So before we get to the NER and linking, we also had a rule-based string search component. So we were provided many examples of how data sets from the knowledge base were referred to in the training corpus. So we search over papers for these mentions that we were provided. And then these kind of come with candidates for what data set they connect to because we were given them as an example for a specific data set. However, these are not like correct right off the bat. So as I mentioned, a single mention could be an example for multiple data sets, and it doesn't, not in every case is it the correct example for all of those data sets. Now, of course, this string search is not going to generalize to data sets that we don't have examples for and data sets not in the knowledge base. So we also have a named entity recognition component, and this is a learned model. Specifically, it's a bidirectional long short-term memory with a conditional random field layer, a fairly standard neural network model for sequence prediction. And so what this does is it reads over the paper and it predicts where the textual mentions in that paper are. So it'll predict that the text monitoring the future from a specific place in a paper refers to a data set. And this was trained on the kind of weekly supervised data that we have from the training corpus. And so as I mentioned previously, what this means is that we search the paper for occurrences of the example mention that we were provided, and then we take those as positive examples. So this is weakly supervised and noisy because that text may occur multiple times in the paper, and these may not all be good examples of a dataset usage in a paper. So once we have these mentions output by the NER model, we need to generate some candidates for what they're going to link to in the knowledge base. To do this, we iterate over all of the datasets in the knowledge base and score them based on how their title connects with the mentioned text. Specifically, a TF-IDF weighted token overlap between the dataset title and the extracted mentioned text. So what this means is that mentions that have many words in common with a specific title will score highly, and mentions that have rare words in common with a title will score highly. A couple examples here. So monitoring the future 2006, monitoring the future survey from 2006 scores highly because there are 4 words in common, and monitoring future in 2006 are all fairly rare. Whereas American Community Survey 2009 and National Survey would score lowly because even though there is a word that overlaps, it's a really common word and appears in probably half of the dataset titles. So once we have these candidates, both from NER plus candidate generation and the string search method, we need to figure out which of these candidates are actually correct. So to do this, we use a gradient boosted trees classifier that takes as input a candidate. So the candidate is a mentioned text in a dataset pair, and then outputs the probability that this pair is a correct extraction. And it does this based on a set of hand-engineered features. So these are things like whether a year appears near the mention and in the dataset title, the length of the mention, whether certain keywords appear near the dataset mention, things like this. So I'll get into some results from this method. So for the NER evaluation, we constructed a test set that had disjoint datasets between train and test. So datasets that were in the training set wouldn't appear in the test set to get a better idea of how this is doing. We can see that there's a lot of room for improvement here. So there's a few pieces of this. One is that it's not generalizing as well as you would hope to datasets that it hasn't seen before. And the other component is that due to the previously mentioned sources of noise, it's not entirely clear, like the evaluation set is also noisy, so we don't know exactly how good these numbers are. So we also performed the end-to-end evaluation that the organizers ultimately did. So on the development set that we were provided in phase 1, we can see that after candidate generation, we have high recall and low precision, which is what we want. We want to get a lot of candidates and then later discriminate which ones are correct. And then after we run them through the classifier, precision and recall balance out and the F1 score goes up significantly. However, we also discovered after the phase 1 evaluation that the development set that we were provided was not extremely representative of the actual test set. So in particular, it had significantly more data sets from the training set than the actual test set did. And so we also ran evaluation on a subset of the phase 1 holdout set, and we can see the same pattern holds, but the numbers are significantly lower. So some limitations of this system and approach. As we've seen, it performs much better on data sets that it has seen examples of, which is not particularly surprising, both due to the string search mention identification and the noisy training data for NER is preventing it from generalizing well. So it tends to recognize things based on syntactic clues. So acronyms, mentions it as seen before, and noun phrases that contain words like study or survey or other like strongly indicative of a data set words. Whereas what we would hope is that it would learn semantic clues and it would actually pick up on the sentence structure or phrases that are used when a paper is saying we used this data set. And then lastly, each data set candidate is scored independently in this model. So there could be added gains from kind of scoring globally across a paper. So probably some data sets are more likely to occur together or to not occur together. Now I'll move on to our approach to method extraction. The task here is take as input a paper and output methods that are used in this paper. As previous presentations have mentioned, we didn't have any data for this. And it was also somewhat unclear to us what a correct method extraction looked like, which made kind of iterating on anything very difficult. So we took the approach of using the Sage ontology that we were provided and some simple rules of things that we kind of expect to look like a method, and then filtering these to be high precision. So we wrote rules to search for the sage ontology. Some examples of what's in here: bivariate regression, longitudinal analysis. We've seen some other examples in previous presentations. And then we also search for phrases that end in kind of common method words, so analysis, theory, model, things like this. So this gives us a set of candidates, and then we want the actual output to be kind of high precision, so that given that we don't know exactly what a correct method extraction looks like, it's hard to do any automatic evaluation, so we would prefer to output things that we have higher confidence in being correct. So we filter down these candidates based on some hand-designed rules, things like capitalization, sentence length, word length, and then also kind of how rare, again, the words are in common English usage. So we prefer to output kind of rarer words as opposed to something general like statistics, say. Some results from this. So we did a manual examination on a subset of the provided development set, noting that this was our subjective view of what was a correct method extraction. So this had very high precision and yielded about 1.5 methods per paper. And then there are some obvious significant limitations to this approach. So it's not going to find anything that's not in the provided ontology, be it SAGE or some expanded dictionary, or matches one of our patterns. And iterating on this was difficult because there was no way to evaluate it, and it was unclear exactly what a successful method extraction looks like. So I'll move on to our field of research prediction method. So the input here is a paper, and the output is a field of research of the paper. And this is not against some set that we were provided. This is just, broadly speaking, the field of research of the paper. So our approach was to train a text classification model. As mentioned before, we didn't have any labeled data for this. So we went and found some, specifically the Microsoft Academic Graph. So the Microsoft Academic Graph is Microsoft's graph of papers and authors and citations and things like this, and importantly for us, topics or fields of study. And then papers in MAG are tagged with these topics. So because this forms a hierarchy, it goes from most general topics down to more specific topics. So we take the top two levels. L0 is the top level, contains things like economics, medicine. Then we can see L1 is a little bit more specific, things like econometrics or intensive care medicine. And then we train a text classification model on this, specifically a BiLSTM with Elmo word embeddings. That takes as input the paper title and outputs, it's two classifiers actually, one for L0, one for L1. They both take as input the paper title and output a prediction for each of the levels. So because the L0 prediction is more general, there's more training data, the categories are more distinct, we always output this prediction. And then for L1, we only output it when the model's confidence in this prediction is high. Briefly, some results on a held out set from MAG that we created. L0 had 84% accuracy and L1 had 65% accuracy. And then some limitations of this approach. So it only makes use of the titles of paper when predicting field of study, and presumably richer information about the paper would be useful. This is because we were only able to access the titles of the papers in MAG, and this was the source of labeled data that we found. And it's also limited to the field of study that MAG has identified. So this is a fairly broad set, but it's not going to come up with its own new fields. So now I'll touch on some future directions for this work. So for dataset extraction, the most promising avenue is improving the named entity recognition model and hopefully removing the string search component completely to help allow the model to generalize better. And we think that this would require having higher fidelity annotations. So actually labeling the text in the paper would be very helpful for examples of what a dataset usage looks like. And this would also help more clearly define the difference between a dataset reference and a dataset usage. And perhaps this would also include some human-in-the-loop method of improving the model, like output predictions, see if they're correct, get more annotations, continue. For method extraction, we did briefly try using an open information extraction approach. Not conclusive that it didn't work, we didn't have it work. And collecting more examples of what a successful method extraction looks like, at least for some evaluation measure, would be very helpful here as well. Then for field of research prediction, it would be helpful to include more than the title into the prediction. So you can't always tell from the title what a paper is about anyways. So including the abstract text, keywords, journal, authors, as much information as you can get would be useful. And the difficulty here is finding a source of labeled data that has all this information. It sounds like maybe there is one, but. So I'd like to thank the rest of my team for their work on this competition and all the organizers and sponsors for putting it on and bringing us out here. And I'll take any questions now. Thank you.
So I guess I'll start with a clarification question.
Yeah.
So when you're doing the dataset identification, what's the scope of the finalist TM?
Meaning, what does it search over?
Yeah. Or are you feeding in sentences at a time? Or?
Sentences at a time, the whole paper.
Okay, and how are you determining sentences?
We used Spacey.
Okay, yeah, so how, I wonder how good is Spacey at, on this noisy data particularly, how good is Spacey at getting sentences?
So it's actually okay. And
okay.
Also, we have, one of the other things that I've worked on a little bit was a version of Spacey for scientific text. And so that involved writing some extra tokenization rules that are specifically for handling citations and such. And so this also presumably helps. We used those extra rules.
Okay, great. That's exactly
I think
what
the
I was
sentence
going to ask
segmentation
about.
is not terrible and not amazing. And obviously there are a lot of random characters in the PDF.
Yeah. Okay, yeah, the other clarification question I had was, so just to double check, you trained on the Microsoft Academic Graph titles and you also tested on just the titles.
Yes.
But you have more than the titles on the test set, so
Yes.
did you try running the system on everything that you had? Or more than just the titles? So like you have this classifier that was trained on titles,
Sure.
you could test it on the abstracts.
We did not try that.
Okay. Yeah, I would be curious to know if that would be different, and maybe you would want to fall back from a bias TM to a like bag of words model.
Sure.
Because like the language of abstracts and the language of titles are different, but maybe the keywords would still carry over.
Following on the same vein, I was going to ask basically the same question, but then I was going to say, if you only have the titles, maybe you could use them to bootstrap other information by searching some other repository using the titles and see what they come up with. You did well, so obviously what you're doing was right, but I'm just curious, for the same commentary I had before, to what end could you improve it by modifying what you're doing in the sense of either more information or extracting, removing some of the nonsensical parts of the titles? For example, a lot of times you have this little flare. Wow, echo. Gone.
Remember Waldo?
Yeah, I guess. Or a voice from above. Voice from above.
Yeah,
No, anyway, that's the same.
I didn't actually work on this component of the system, so my answer is going to be very high level. I expect that abstract and keywords would help a lot. Just looking at some examples, you can see that the title is not quite enough information to figure out.
Keyword you may already have from the words from the title, a lot of them, but
no, these are like search-oriented keywords.
Yeah, okay.
Yeah, so they're specifically intended to help people find this paper.
Okay.
So yeah.
Yes.
Just FYI, there is a way to get to the abstract through the Microsoft Academic Graph.
How would you know that?
I just looked it up.
It's funny because we did work with someone who works on it, so I don't know. But yeah, we'll look into that for sure.
Similar question I asked on the previous. What types of errors are you seeing?
So for
the data, specifically the data set extraction.
Yeah, that's good because that's what I have answers for.
That's fine.
So for the named entity recognition piece, as I said, it's mostly picking up on syntactic clues. So this leads to a lot of errors around this. So it has a tendency to think that acronyms are data sets, kind of somewhat universally. In particular, there's one acronym.
Sage.
Yeah, we probably should have just filtered it out, but you know, it's a publisher and a data set, so it appears in like every paper. And then there's also, as said previously, it also sometimes predicted organizations as data sets. That was another error that we noticed. And then there's also a component of outputting data sets that the labels don't consider to be used in the paper. So sometimes if a paper says like, we compare against previous work that used dataset X and we used dataset Y, our model might get both of those, but only one of them is considered correct. I'm not sure what the like actual ground truth would be, but I think those are the main sources of error that we saw.
My last question, which you were expecting, which is a big unfair for you, but what did you write wrong and how would you do it differently?
So I think that the NER plus candidate generation plus linking is a reasonable approach, and I think that it can be improved significantly beyond where we got it to, with refining the data, perhaps some weekly semi-supervisor code-training as you suggested previously. In terms of what we did wrong, so like one thing that I learned from this competition, I'm a bit new to research in general, but look really hard at the validation data set before you do stuff with it. So the validation data set that we were provided was not representative of the test set, and with some more careful examination, we could have figured this out. But we spent a lot of time iterating based on the results from the validation data set, which ultimately, I mean, I don't know how useful it was, but obviously working on a validation data set with a more similar distribution to the test set would have been helpful. And then lastly, also would have...
That's true for everything.
Yeah. Yes, of course.
Yes, you should train better. It works better.
Also, I would have spent much more time with the weekly supervised training data and improving that process. So there are certainly a bunch of things that could be done, like figure out where the citations are and don't positively label stuff that's in the citations, or only take the longest one or the first one, or exclude abbreviations, a bunch of potential avenues here. I would have spent much more time working on those at the beginning.
Thank you.
Alex?
Only a short question, maybe. You said you didn't work on the research field classification, so I don't know if you can answer it. But maybe you know it. Did you try to use the results of the level 0 classification as an input feature for the level 1 classification?
No, I agree that would be useful.
You said that you used Spacey for sentence segmentation. So how long did it take you to segment the sentences in publications in general, if you have any idea of that?
So for those of you who don't know, Spacey is a commonly used natural language processing library for kind of the lower level NLP tasks, and it's heavily optimized for speed. It's intended to get close to state-of-the-art results, but be really fast. I want to say it took an hour and a half or 2 hours on the 5,000 papers, and this was to run like everything that's in Spacey. I mean, we took out the NER because we weren't using it, but the rest of the Spacey pipeline. That's what I remember. It could be a little wrong, but that's what I remember.
Anything from Franco? Franco or Ian, do you have any comments or questions? Okay, well, thank you very much. Great job. Much appreciated. So we're going to break for lunch now and come back. The judges are going to go.
Not for me, thank you.
Okay, thanks, Frauke. the lunch, there's box lunches here. The judges, we're going to go upstairs into the Lafayette conference room, so we'll walk up there and over towards this side of the building on the 3rd floor. And then we'll be back at 1 o'clock-ish to announce the winners.
And we should grab lunches.
Yeah, you can have lunch. And coffee. There's coffee
Judge
too
first.
off here. Okay, thank you very much. Okay, so thank you very much. Thanks for a great set of discussions. The judges met, and we actually decided to flip the order a little bit. What we thought we would do is go ahead and announce the winner first, so that you're not sitting and listening and wondering what's going on. And then what we'll do is Jonathan will tell you a little bit about the protocols that we used. Recognize, of course, as you all noted, that because we had a zero baseline, right? If I hold up a document, we can't tell you. That's the whole point. That's why your value is so high. Understanding that the actual calculations that we made are reasonably noisy. So that played a part, but not a full amount of the discussion. So he's going to explain kind of how we did some of the initial tests. The judges are going to talk a little bit about the reasons for their thinking. And the focus is going to be primarily on the dataset identification, because the fields and methods was kind of this would be great to help us, but not the core focus of the analysis. Then I'll talk about next steps, and then we'll have some photographs and congratulations, and then networking up the back. So we've flipped the conversation a little bit. Okay, so with a drum roll. So we're going to say you guys should all be congratulated. We had, as you know, 20. Yes, we were thrilled. We were absolutely thrilled, and I think the judges, both the social science judges, Frauke, our colleagues at the Deutsche Bundesbank, and I, and then all the people who did the judging from Health and MDRC and Chapin Hall and so on, you guys did a fantastic job with a very complex and difficult task. So my opinion of computer scientists has increased over the very low baseline I already had. So we want to say, you know, there were 20, then 12 submitted usable code. We selected 4 finalists, so you guys are already winners in many ways. We decided to change the given the comments of the judges, we thought we'd actually do an honorable mention as well as a winner. So the honorable mention goes to the KAIST team. So we were... And then I wish we could give you all the winning tag, but the winning is Alan AI. So thank you very much. So Jonathan is now going to talk through, and we will print certificates and send them to each one of you. And Jonathan is now going to go through and talk through how the scoring was done, how we got the human curation part in there, and then the judges are going to speak.
So briefly, I don't have a microphone. Hello?
Oh, here you go. I was walking up with it.
That's okay. Okay, so briefly, the score, we made scores. We tried to make a quantitative judging. It is a component of the judging, but it wasn't all of it, and you'll see once I describe that some of it is a little fuzzy. Given, it's great that we had good real-world data, but some of the limitations of the data made some of these scores a little difficult to interpret, at least. Let's see, so we made 2 sets of numbers for each team. I don't know how to do that.
Windows P and then duplicate.
Windows P and then duplicate. Okay, Windows. I'm a Mac person now. Windows P And then, awesome. Oop. Okay. Thank you. I don't hate Windows. I don't use Windows very much. Okay, so. Oh, yeah, how do I go? Thank you. Yes, obviously I'm well prepared for my moment in the spotlight here. So we had two sets of data that we tried to create. One was a set of precision and recall scores. Can you read that? It's a little small. Let me make this go away. Well, oh yeah, here. Oh, well that wasn't what I wanted to do. Yeah, okay, well anyway. So we tried to make precision and recall scores. And against the phase 1 holdout. Which one? Do I really want that? No. Wow. All right, I'm going to be a Windows Pro by the time I get done. I'm very excited. It's a great operating system. Lots of people use it, I swear. So we tried to make scores. We wanted to make some indication of numbers that people would know how to interpret if they know machine learning. So for the phase 1 holdout, we were judging the model's performance based on the citations within publications that were present in that ICPSR data set. So these were just the ICPSR data sets that ICPSR had said were used for analysis within the publications. So this is the data that we gave you to train on. And so we ran your models in phase 1, and then in phase 2, we ran your models again over that same holdout corpus just to see how the scores changed. And so that's what those precision and recall scores are for phase 1 model holdout 1 and phase 2 model holdout 1. Because our second phase holdout was wild, I like saying that, it makes me laugh, wild. Because our phase 2 holdout was wild and we didn't have any of that pre-coded, we went for something that was a little bit different. I'm going to switch over to the tool. We picked 20 publications from each of 6 topic areas, like education, business. So we picked 120 publications, we ended up with 123. And then for each of them, let's find, we had human coders go through and in each publication find every mention of data. So in terms of interpreting the scores, we'll get you a summary of this also, and details, more details. But in interpreting these precision recall scores, in the second phase, we went through all the publications and had a human coder with all of the potential error that is possible there, try to capture all the places where data was discussed. And so we moved past just formal citations of ICPSR data sets where the data was used in analysis. And for this phase, because we had to start from scratch, we looked for places where data was mentioned. So there's 3 types of data reference that now are present in this system, in this data set. We have places where a formal titled data set was mentioned. It could have been used in analysis, or it could have been just cited in a literature review or something like that. There's the kinds of data that that authors of publications create in the process of doing a study. And so that could be medical tests in a medical study, or it could be a survey that was given to participants. And so not titled data. This is not something that necessarily your models were, not anything maybe you were told about, but we were trying to start to make the next data also and see how the models performed. The next data we're hoping is going to have titled data sets, whether they were used for analysis or cited and mentioned, and then also include places where data was created and that discussion around data, probably 2 separate models, who knows. So each team's mentions for a given publication, which is what you'll see on the right here, were then hand-coded as to whether or not they were related to the data set reference that's on the left in this tool. So the precision and recall scores you see on this summary, and we have a relatively formal protocol But because of the different types of mentions and because the teams weren't really told that this was how we would be evaluating, we tried to be relatively flexible. And so, I'm not sure if the hand grenade analogy is a good one, but we didn't care if paintball, water balloon. We didn't care if the water balloon hit someone on the head. We wanted to see if the person got wet. And so the radius of related was relatively large. We tried to be relatively generous, just to get signals out. Partially, we wanted scores, but given the time we had and the data we had, we were trying to make sure we could at least, at the very minimal, say this article had data, did the teams find data or not? It ended up we got better data, so we were able to do some of this. But so these scores, there's a lot of different ways they can be interpreted. And so we'll give you more, I'll write up more details on each of your performances, but this is a part of our evaluation, but because of the noise in the data creation and the fact that the models weren't really designed for this, this is a part of our evaluation, but we didn't say whoever got the best score is the winner, hands down. This was definitely relatively ambiguous, and so an input, but not a firm decider. So that's how the precision and recall data. So phase 1 holdout, it was citations that were used for analysis from a set of citations, and if your model found mentioned data sets, then that would be counted as a false positive, even though it was a true positive. If you found other data sets, that also would be a false positive. In the second phase holdout, we had this different data that allowed for matches based on mentioned text or on citations or both, and they were all kind of counted equally. So when you see the scores, just to help you understand, these are relatively fuzzy. You see precision and recall and you want to say, number, I can order those numbers and that's who's the best. This is not that. They are numbers. You can't order those numbers, but there's a lot of different signals that can come out of these numbers, just so you understand. Any questions on that part? I talk very quickly also. If I'm going too quickly, please. One of the teams didn't generate the citations for the second phase, and so we couldn't calculate their scores. And so that's actually, since we asked and I said it, it's an interesting indicator of the ambiguity in these scores, because the mention text that Team 17 created was good enough in terms of all those different types of data that it didn't hurt them to not have any citations in the second way we did precision and recall. And so, and they did very well. Like the types of text, I was really excited to see your presentation. I'm not looking at the right people, but the 17, I was really interested in how you did what you did, because it turned out really well for this. And so, so that's a breakdown of how this all worked for this type of data. Then briefly for the qualitative, I'm not going to be a Windows Pro by the time I'm done today. That's a shame. For the quote-unquote qualitative, for more of the social science judging, we took samples of publications, and then for the different types of data that was being created by the models, we placed the results from the teams side by side. And then the judges went through and chose whatever heuristics they wanted to assign +1, -1, or 0 to each of the teams, and then summed the scores, and then used that to make rankings per judge. And so there were rankings. If you look at the scores, we'll send you the summary of the scores. It's interesting. Like, there were some very different heuristics, obviously, because some of them were mostly negative, some had a really broad range of scores, some were very tightly packed within maybe 10 of each other. But the idea here was that we tried to take two samples. One was the same that we used for the precision and recall, and then the other was a 60 where we looked at agreement and disagreement across teams for data being present in publications. So we picked 10 where all the teams agreed there was no data, 10 where all the teams agreed there was data, and then 40 where we picked and chose one thought there was, 2 thought there was, or 3 thought there was, so that we would have different characteristic, like different states of publication based on agreement. And then we'd use this tool to review the mentions across those. And so you can see we'd had mentions, we looked at fields the same way, and we looked at methods. And so then those were the numbers that we created to start our discussion in terms of judging. Again, given the data, given how subjective a lot of this was, we weren't making this the end-all be-all, but this is how we made data to try to quantitatively assess performance of the different teams. So any questions on this other second half? Okay, so that's all I have unless you have questions. I think now we're going to go to having the judges give you their feedback.
I guess we can do it from here, Drew?
I think so, as long as you have mics.
Oh, wow. Has this mic been on the entire time or off? Doesn't matter. First of all, let me start with the basics. Congratulations. There was a group of you that started, and there was a group that, from the group that started, there's the 4 teams that came here. And every one of the teams did something that I found interesting and different. Clearly, the team that had the consistently high scores in precision and recall, the Allen team, did a beautifully engineered, beautifully systematic, beautifully rigid, reproducible, well executed in terms of a use of resources approach. So I congratulate you, and you guys, as Julia said, won. So congratulations. The KAIST team, I am pretty impressed. I'm a engineer at heart, also my background, but engineer at heart, and I very much appreciate a widen and reduce, or branch and bound, or whatever you want to call it, approach that was beautifully done, that moved you from was poor scores to fantastic scores in a matter of months. If I could do that with my students, my students would be very happy. Hell, I'd be very happy, but I don't do it.
My wife would be even happy.
No, my wife would be happy if I wasn't there. She's happy I'm here. No, the team from Leibniz, I was impressed. You basically harnessed all the resources that you could get, and you utilized it exceptionally well. The ability that you actually had access to it, but one of the cardinal rules in developing a proper system is use what your talents that you've got and lose the resources that you've got. And you guys actually had the resources and used them well. So again, I applaud you. And finally, I want to applaud the team from Paderborn. You basically used a very, 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 very methodical, tried a large number of variations. And if I was going to lead an effort, I would definitely make sure that all the people in my team tried all the possibilities that they have at their disposal, and you guys really did that. Ideally, I would have the 4 of you put together a team and do it all in one shot. And I'm sure between the combination of engineering and approaches and utilization and so on and so forth, it'd be a fantastic effort. So again, I just want to congratulate you all. It made my job, our job, but I'll speak for myself, much harder, given the differences between how each of you approached it. And I, for one, learned a lot from it. So I want to thank you for the opportunity to be involved. Thank Julia for the opportunity to be involved, and for the teams to be involved, because I learned quite a bit of it. So thank you.
I can go next. Yeah, I guess first I'm really glad you guys took part in this, right? Because you could have done a Kaggle competition instead, and that would have been a wonderful waste of time, because the key things about this was a real problem that somebody actually has, This was real messy data that exists as it is. It hasn't been cleaned, it hasn't been turned into a matrix for you to run your for loops on. And the evaluation was unclear, right? You want to build something that you can see, is it useful? And that's where I like about, also from sort of Julie and Jonathan setting up the evaluation so that it reflects a little bit of how it's actually going to be used. You're looking and say, is this data set, if you told me this, if I was searching for that problem and I would get this data set, would I find it useful? Which those evaluations are expensive, they're subjective, and they're hard to optimize for from the developer's side, right? Building it, you can't really optimize for that, which means that all the ingredients that go into deciding to participate in this has to be you care about solving these problems. And so that's, I think, really important. And I'm also hoping that for future iterations of these things, you can sort of propagate that excitement to other people, because I think we need more people in this area to be working on these problems rather than the standard data sets that everybody works on. Right? That's useful for benchmarking. It's not useful for doing new things, and I think so that's really exciting. I think for the specific things that, as Ophir already sort of mentioned, the things that are really good about. So I don't want to. I think a lot of us will repeat the same things because
that's why I wanted to go first.
Those were the things that we really liked about a lot of the systems. So that's why I kind of mentioned two things. One is, just to reiterate what Jonathan said, don't take these numbers too literally. We didn't. So in our evaluation, we weren't looking at those things for a significant part of our discussion. It was really other parts of it, the qualitative part, this part, looking at the code, looking at the approaches you used. And honestly, we were all sort of, the presentations this morning were extremely useful, right? So yesterday we all met and we didn't pick the ranking and the winner then. That was the idea. And we thought, well, let's wait till because it was really close. And the presentations today made a lot of things much more clear. So one little feedback is, for the teams that presented stuff, try to give that as part of your submission to make it easier, because there was a lot of information you presented today that wasn't in your write-up. You guys were all extremely clear and descriptive on what you did, and that was really helpful for us to look at. The only thing I would say, which none of you really did, because it's not standard in IR to really do too much of that, but I would say all of you are sort of putting in precision recall numbers as if they are absolutes, right? You chose an arbitrary threshold, and sometimes Jonathan did, but all of you sort of picked these things, and for if you don't know how it's going to be used, you can't pick that, right? So I would sort of push back on the organizers, even ask like, how do you want us to decide that? Which one do you care about more? Because it's not, looking at these numbers, like just take the 1154 and 1617, or the 5% recall at the expense of 30% precision could be really important, or couldn't be. I don't know. And I think from the judging side, these numbers, that's why it's really hard. But even for you guys as looking at a problem, that threshold is so arbitrary that I would sort of just be more careful on those things in general. But yeah, so I think good job of getting this far, doing the whole thing, and yeah, having the code publicly available, because I think that's the other thing that will be really valuable to the community, is being able to take what you guys have done and building on top of that. So congratulations.
Pile on that a little bit. Yeah, I mean, I think that one of the things to take away from this, as Ian Mulvaney, who's on the phone, said earlier today, said the real world is messy, and a lot of you sort of alluded to the fact that the data were messy and some of the labeling was inconsistent, and that's reality on the one hand. And the other thing to think about here is that you guys were in many ways guinea pigs here in us trying to figure out how this can and should run. So one of the things that we've been talking about, and one of the things that may come up in the follow-on next steps session, is we'd love to get more feedback from you guys on what could have made this run better and how we might do this again in the future. And if you think about some of the ongoing challenges that have existed, the NIST speech-to-text challenge or the TREC annual competitions where there's a consistent set of tasks, ACL's shared tasks as well, a consistent set of tasks and a consistent way that these things are scored and evaluated every year, and getting to the point where looking at an F1 score, for example, despite what I says about the thresholds, is actually meaningful to know that we are progressing, you know, this many points year over year. And you guys have sort of set the baseline here, and if we can really formalize this challenge, really formalize the task going forward, then hopefully you and people who are on the WebEx and people who will look at your code and see these presentations will be able to start putting these approaches together, applying new approaches, and say, hey, I think I can get a gain here if I look at this a different way. So we still need more input from you guys, I think, to understand exactly where the bounds of that challenge are. A lot of you spent time in doing the PDF to text parsing and stitching and other things, and I realize that's probably not where we would want you to be spending the time. So what are the formats that would be helpful? Would it be more useful to have an online submission form where you can actually iterate multiple times and get feedback from a held back corpus at the risk of overfitting your model? But you know, these are things that I would love to learn more about as we talk about next steps. And then I guess the last thing, just in terms of, you know, feedback to the teams and also for us learning about this competition, it was discussed the distinction between a mention in the text versus a usage. And I thought that Alan AI in particular really sort of went that next step to say more than this data set was mentioned in a text, but this was actually that this paper used this data set. And so if you start looking at it not through a specific use case, but what we're trying to sort of stitch together is a set of relationships between publications and data set, and really not just a mention, but a usage, I think is probably where I would like to see us emphasize more in the future. So awesome stuff. It's wonderful to see how different teams drew on different data sources to bring in, nice. I'd love to get the same group of people together in the room and say, okay, now let's do round 2 and take the best of all of our approaches and see what we can do with that.
A couple hours left. Yeah, so I'll try not to repeat what has already been said too much, and so first of all, okay, I will try not to.
Perfect.
So first off, thanks to all the teams for sharing your techniques and your insights, and especially your code. I know code is a very sensitive personal thing, and to know that someone else is going to be looking at it always makes me nervous, and so I'm very grateful that you all shared your code with us and let us take a look at all of your beautiful, elegant code and your dirty hacks and how they weave together into stuff that mostly worked. So just specifically on each of the teams, I thought Paderborn really did a great job on focusing on the problem of pre-processing and really highlighted a lot of the issues there that are obvious in hindsight, but obviously were not clear at the beginning. For Leibniz, I really appreciated the write-up and the documentation, and that was very clearly the best. It articulated why you did things, what happened, and it was very easy to understand what you did. And for things like this, the goal is for other people to carry on the work, and I think this team did the best job of making that possible to understand why and how. For KAIST, for the other submissions, I would read through and, oh, that's why you did that, okay. And KAIST really was a mind-bending experience. I was so surprised. It was very ingenious and completely unexpected. And that's one of the beauties of formats like this. So somebody comes with a problem and someone else comes with a solution that you didn't expect. And that's a kind of surprise and ingenuity and innovation that this sort of event is designed to create. So that was amazing. And so like I work on question answering, and I was completely surprised that someone would try to do question answering here, but it worked, and that was beautiful. One of the other judges Frauke said that it looked like someone reading a paper. So that I think is high praise, that the output looked like what a human would produce, and that I think was also a surprising and great outcome. And finally, for AI2, this was a system that could be used tomorrow, and very well designed, a good use of state-of-the-art NLP techniques, thorough engineering, solid, sensible design that worked and worked well, both in terms of quality and efficiency. So really a tour de force, focusing on all aspects of the problem, did everything well, and a winner, but surrounded by stiff competition. Again, thanks everybody for your participation and all of your hard work and your insights, and I'm honored to be a part of it.
Thank you very much to the judges, and I have to say, they've been friends for a long time, and I'm very glad that you're my friends. I'm very glad that you helped us design the competition and all your thoughtful input as we were going through. Any comments from the teams? Okay, so I'm going to go on to next steps. The gentleman who just walked in is Stu Feldman from Schmidt Futures, who is another one of our sponsors, and his flight was delayed from California, so, and the red eye, so he's a little bit late. I'll ask you to say some, do you want to say a couple of things? Okay. So I promised we'd go through next steps, and oh, yes, let me reiterate the winners and the drum roll. Where's the drum roll? Yeah, really. So the winners are all of the teams, just to reiterate. The honorable mention is to KAIST, and the winner is Alan AI. And after I've gone through our next steps and a word from our sponsors, I feel like Masterpiece Theatre, I'll try and get a better English accent, get rid of this New Zealand one. We'll have the photos of all the teams and the sponsors to kind of conclude, and I believe we'll have refreshments and a bit of chat afterwards so that you can interact with the judges and get feedback. Okay, so what are we going to do for next steps? So we're going to send you, Jonathan and Drew. Yeah. And I will write up the detailed results of the phase 2 scoring. Part of where our naivete on this is we had no clue. I mean, Jordan, when I first, they all kind of said, oh yeah, this is going to be a lot of work, and we kind of processed that in a different timeline than we had anticipated. So the work of the scoring and all the coding and the result getting was very compressed, much more compressed than was probably optimal. But we will send you back a detailed piece of information when we get done. As I explained in the beginning, this is the beginning of what we think of as a fundamental change in the way we do empirical social science research. This is the first attempt to try and read publications and figure out what data sets are in there and create that link between data sets and the scientific conversation. So very much part of that is going to be our work with dimensions, with providing that plug between the data set publications that are generated out of your models and fed into that, and building a engagement loop with the community. We're going to start with 3 communities, and build an approach that can, we hope, scale to other fields. So part of our goal here is to scale to many other fields. So the Deutsche Bundesbank has generously agreed to work with us on reaching out to the finance community to develop corpora that are tagged with datasets, DOI links, and validation using the tools that Daniel and Thiago and Graham developed and that Jonathan described, so that they can, will pop up a prediction or a recommendation, and someone in that field will say yes, no, or it exists. Our partners at the US Department of Agriculture, who are, I believe, coming in, who are helping to inform the White House Federal Data Strategy with Bryant here, will also be helping to reach out to the agriculture community to do the same thing. Eric Miley from Overdeck volunteered to pull in the education community to develop much better curated education links for the education research community. And if anyone is listening from the webcast and wants to volunteer a community, then we'll do the same thing. We'll also work with, as you know, SAGE, providing recommenders as people are submitting articles, and have the people who are submitting articles validate whether or not your prediction is correct, and curate the data set. And my co-PIs, Brian Granger and Fernando Perez, and Raphael, who is not here, are working to link Daniel's DFAdmin hooks from what you're producing in what your model is predicting into our data model, and use that to feed into the dimensions and get the feedback loop. So our focus over the next 3 to 5 to 6 months is going to be to get what you exactly identified as a core weakness with the messy data, is a better human curated corpus. But what you did was you got us from a 0% baseline, 0, to 30, and in some cases as much as 50%. That is amazing. So you've made a huge leap in our understanding of how to do this. Here's what we're going to ask you to do. We deliberately didn't ask you, we didn't give you a corpus of methods because, frankly, the current corpus that was developed by SAGE, the one that we put on the website. And we thought it was a great start, but we thought that maybe other people looking at publication data might come up with some imaginative ideas. I mean, I have great respect for the imagination that you guys all showed. Maybe there are other ways of characterizing methods than the human-curated taxonomy that was developed. SAGE would love for you to provide input into how to get better measurements. And a couple of you correctly said that the problem with using a preset taxonomy is it doesn't allow you to identify new methods and ideas. So to the extent that you design ways of bubbling up, oh my gosh, there's this new method that's being developed, how cool is that? And it's being applied to climate change, maybe we could use this in another area. A number of you used, and Ian Mulvaney would love to get feedback on the methods and the fields. You all imaginatively made use of external data sets, and we'd love for you to communicate with each other about how to improve your methods. I think, given the amount of interest that this work has generated here in the United States and internationally, one of the things I've learned, you guys are a little bit junior to me, but one of the things I've learned in life is if you hold stuff in to try and get an edge, that's completely the wrong approach. You need to give out, you need to share, you need to build a community in order to create a community. So I'd encourage you, rather than to hold on to your methods. And really, the computer scientists are very good at this. You're very good at sharing and building knowledge and so on. I'd encourage you to keep a conversation going among each other. You were very gracious to us in your comments about the way in which we structured the competition. If you would gently provide comments to us about how we could improve next time. My beloved colleagues have already made some trenchant observations, particularly of fear, I'm looking at you, about how to do things better. So the future, the book, as I said, that SAGE has agreed to publish. You've all given us white papers. We'll be back in touch. I provided the schedule beforehand. Jordan convinced us that this was the beginning of what should be a regular event. So our thought is that in 2020, we'll work to develop better models and tools and a better human-curated corpus, and then have another round of this competition, sponsors willing, in 2020 to figure out how whatever we built can be improved. So the rinse and repeat approach. And then finally, you guys are amazing. Thank you so much for everything that you've done. Ophir.
Yes, it's on now. I just want to say one last thing. I want to actually congratulate Julia and company for a truly remarkable, and I do mean unbelievable, success, in many senses of the word of unbelievable. This couldn't have happened without your curiosity, dedication, and ingenuity. So I think we should give her all a round of applause, and for the rest of their crew.
Yeah. And it should be directed to Jonathan and Drew, and for heaven's sakes, Emily and Orande, as you go out the door, they've done an amazing job of organizing all this. But Stu, would you like to make a couple of comments on behalf of the Schmidt?
Yeah, I'll just say a couple things. Sorry to have missed the fun part, but I'm hoping there will be replays available of the competition. First of all, we're just delighted to be supporting one of Julia's many overlapping efforts to basically make hard data available and usable, and find out why and how. This competition is one approach to looking at the literature. About 10 years ago, when I was at Google, a couple of my colleagues figured out they would do a nice project of trying to extract sort of all the published tables in books, and figured it would be about a 2-weekend project. Didn't turn out to be that easy. You'll hardly be surprised. Yeah, and Google at least had copies of the base OCRs. The reality of actually being able to look at the wild literature, extract what it says, what it thinks it's based on, and then actually finding the places that it claims to be true. I'll just point out social science is only one of the areas in which we don't know how to do that very well. I just came from a meeting where a bunch of people were attempting to make sense of a commercial database of 35 million chemical reactions. And one question was, what fraction of them were right? And they were all previously extracted from the chemical literature, which you might have thought was well organized by substance and reaction. The offline comments weren't very polite. Okay, so this is a huge area of endeavor. The one where it actually applies to people is obviously critically important. I'm utterly enthusiastic. The hard part of figuring out whether the reference is real, whether the reference is saying this data set is bogus versus this data set is gold, little things like that. I've just summarized all of NLP, unfortunately, to get that one right. Is just a wonderful set of problems. I'm really looking forward to how, in essence, you can crack subgenres, as listed here on the previous slide, and others of the social science literature, and in passing, getting a review of what data you might actually want to use in the future and who's actually using it. This is just a great problem, and it feeds into sort of this general goal of how do you improve real research by access to already done work and reanalyzing, redoing. So I'm just utterly enthusiastic. Yes, we are funding a chunk of Julia's work in addition to a number of other nice people in the room and elsewhere, and just happy to be doing it. Thank you, and sorry if I managed to choose the wrong airline.
Your predictive algorithm wasn't too great, huh?
Well, sorry, we managed to get out of San Diego with 30 seconds before the curfew.
Oh my God, I know that feeling.
And let's just say the air was just a trifle choppy. We had a tailwind of over 200 miles an hour.
Oh my God. So, for those of you who don't know, Stu is famous for many things, but he wrote the make function. So, yes.
And claims 0 credits in social science.
Okay, well, so thank you very much. We're going to take photos of all the teams now, so if you'll bear with us, and of course we'll send you the photos so that you can be recognized in your home institution. And we will send certificates and the checks separately, and Arunde will handle all of that. I'm not quite sure how that's going to happen, but they'll sort it out. Okay, well, thank you very much again. We're thrilled. Okay.